Okay.
Just one moment, I'll start recording.
Shall I start?
Just one moment.
Okay.
Yeah, you can. You may.
Good afternoon, everyone. Today I will be presenting this paper, Learning DNA Abstractions Using Gradient Descent. So we already know and we are aware of, we have been made aware in the class that deep neural networks are used in various aspects of life, image, voice recognition, natural language processing, particularly in safety critical domains also like medical diagnosis, autonomous vehicles. So in the safety critical domains, when DNNs are used, we need to have some sort of verification, and there comes one of them is formal verification. And so the vulnerabilities, the adversarial attacks, backdoor attacks. So to have some form of verification, and we will do today we'll proceed with formal verifications of DNNs. So any property, say P, can be expressed as a SAT query. So if n entails P, that means like n should valid P. So how can we say that? How can we check whether this n validates P or not? So we will feed this SAT query to the SAT solver such that negation of P of y, when y is the output of the neural network n given an input x. If this thing satisfies, then we can say there exists an input within the input range such that it violates like n entails P. So we can say that, oh, this is not valid. So to check that, so we will, what we do is like there are different approaches we are made out in class, like complete methods and incomplete methods. But the challenge of this is we already know that SAT is NP hard, and above all, the size of the neural network, when it's large, it can cause timeout and other different like difficulties for the SAT solver to check the property. So abstraction techniques for scalability. So our idea is to come up with an abstracted smaller neural network such that if the neural network say n dash validates the property P, then the actual neural network must also validates the property P. So the techniques which we were made ever in class and another of our batchmate has also presented are the Seeger techniques and the Seeger-like techniques, which are based on merging and unmerging of nodes. And then we merge the nodes and come up with an initial abstraction. And then depending on spurious counter examples.
That's Paranika, correct?
Yeah, that's Pranika has presented. And depending on spurious counter examples, we will keep unmerging the merged nodes. So what is a spurious counter example? Spurious counter example is one such input point which actually satisfies the property in the actual neural network, but it defies the property in the abstracted neural network. So the verification pipeline is there is an original DNN n, then there's an abstracted DNN that is n dash, which we feed to the verifier, and then we see if there is a spurious counter example. This can either it proves the property or it can come up with a real counter example. If none of the two happens, then there will be a spurious counter example, and based on the spurious counter example, we will do the refinement process and continue until we come up with an smaller we come up with an abstracted neural network that if validates the property P, that must imply the original neural network also validates the property P. So the key challenges of whatever processes we have seen in class, and also Pranika has presented that like these are all heuristic based merge unmerge operations, and they fall short in some cases, and we will see in the following slides. So before that, I will say we will pre-process the neural network. For a given node in the hidden layer, if increasing the value of that node results in increase in the output of the neural network, we will call that neural network inc node. Or decreasing the value of the increasing the value of the neuron in the hidden layer cause decrease in the value of the output of the neural network, and we will call it as dec nodes. So and we will follow this notation henceforth. And now we will see how the techniques we have seen in class, the merge operation, is that, okay, in this toy example we have taken, I would like to mention that all the nodes in the inner layer are inc nodes. So we can merge all of them into one, that is A over here. So this is the fully merged neural network. But is this neural network, fully merged neural network, good enough? We will see. So the merging technique is simple, that we will take the maximum of the incoming weight for all these nodes and sum of the outgoing nodes weights, or sum of the outgoing weights. So first we will see for the property P1, that is for all x belonging to 0, 1, we will the output of the neural network should be less than 4. And so sufficient condition should be that the output of the abstracted neural network must be greater than the output of the original neural network. Hence, when the n-x satisfies the property less than 4, we can automatically conclude that n of x also satisfies the property less than 4. Now we will see in the original network, if we feed this input 0, 1, we will get the output 1. But in the abstracted neural network, if we feed the input 0, 1, we will get the output 9. So this is a spurious counter example. We will see with another property. Say for the same neural network I already shown, that is this original neural network. Say the property we are now considering is for all x belonging to 0, 1, n of x is less than 2. So this blue plot we can see here, this blue graph plots the actual behavior of the neural network for these data points. But if we see, we want the property should be bounded by 2. So when we see the green plot, that is it is bounded by 2 in all possible ways. So we can see this is actually 3 piece functions which are divided by 2 partitions. So it is like 3 piecewise linear functions. So and the 2 divisions can, looking at it, we can we can try to emulate this property by 2 ReLU neurons, 2 ReLU nodes. So and actually we can do that. We can actually come up with an optimally abstracted neural network, which is this one, and with 2 inert nodes and ReLU function associated with it. So this actually we can come up with. But
that two node neuron,
Mhm.
what in terms of your picture, this is a beautiful picture. I mean, I should tell you. I mean, is it in the paper?
No, it was in the paper.
Okay. What does it's obviously it's more precise, than the traditional node merging abstraction. Okay, because you have two ReLU. But what portion of this thing that see in this thing, there is some portion which are obviously spurious, okay, and some
Okay.
are kind of overlapping and some things and so on. What portion does this actually eliminate here, and what does it reserve? The keep.
I will go
Now
there.
you will say
Uh,
that. Okay, we'll describe it later on. Yep.
yeah,
Okay.
I'll proceed. And okay, so we actually can come up with this optimally abstracted neural network, but we will see how we can come up with this. Before that, I want to mention that no sequence of merging or unmerging operation can derive this figure, this this optimally
Hmm.
abstracted network. And
Hmm.
we will see how, because see, in the original neural network, if I go there and it is abstracted into one node, so what is the next possible unmerging? It can be, it will get unmerged into 2 nodes. And if another unmerging step happens, it will go back to this original neural network. So the idea of abstracting it to come up with a smaller neural network fails there. So what if we unmerge C naught? If we unmerge C naught and fit 1 comma 1, we will see it will still 6 will be there, and this is a spurious example. And again, for if I unmerge C1, then also their output is 4, and again it is spurious. So again, if we take unmerge C2, again we will see the output is 4 for the same input, and hence it is spurious. So none of the way we could come up with this the optimally abstracted neural network that I just claimed that we can come up with. So what does this say about like the process we are already aware of? So like there are several networks that are not particularly reachable by Sigar approach or the Sigar unmerging technique, because like the if we fail to pick the right unmerge, so ultimately it is when even when we do the unmerging technique, we follow some heuristic. Depending on that, we unmerge one of the node. So the ultimately we're making a choice to which one to unmerge or which to not unmerge. So we can clearly see this technique of like from an abstracted node we are unmerging, and this technique is clearly failing to come up with a good enough neural network. So
I just have a question here. So the previous example that you showed, if I understand correctly, that tells us that in this particular case, for this particular property, no unmerging or no like possible merging following the min-max based methods will give us this promised optimal abstract network, right?
Yes.
So if you consider the search space of all the possible merges that something like a min-max based method will search through, this network is not reachable from that space. That's what you're saying, right?
Yeah, that's yeah. This network is not like we cannot reach there by like in any way. Like the search space of the merging unmerging based techniques will not contain this optimally like at the optimal neural network I just showed. This will not present there, and hence we can say that the technique we are like adapting to get an optimal abstract neural network is also failing, because it is also not like it restricts the search space to some limited neural networks where
So,
there
so
can
min-max
be...
and sum you're talking about,
Yes,
is it?
yes.
What is your question, Diganta?
So then my question is, no. Then my question is that can you just clarify what you mean by the exponential search space here? I don't know if like as in how does
before you explain that, now that Diganta made that observation, and I want to kind of rephrase or kind of understand. So when you say that that node merging splitting strategy, of course the splitting, whether you can reach that optimal or not, depends on what kind of splitting strategy that you use, correct? So I guess you're referring to the specific splitting strategy that is described in the paper, where it considers try to remove one at a time or two at a time and so on.
Yes,
None
exactly.
of the combinations really is able to
come up with the
with that thing. So I guess of a different splitting strategy could possibly have done it, but then nonetheless, that's what you mean. Okay, now go ahead. This to address Diganta's question about this exponential search space.
So exponential search space, because like, okay, so given in the original neural network, if there are certain number of nodes in a given layer, so when we come up with an abstracted neural network, so it is basically like by this merging unmerging technique or any other, like it's come up with like when we are reducing the number of nodes in a particular layer from the original neural network to the abstracted one. So it is like partitioning the entire set of nodes from there, and there can be exponential possible ways of doing the partition. So that's what I meant by
exponential in what? In the number of nodes?
Number of nodes.
But you just now said number of nodes in the same layer, I presume.
Yes, yes. Can I proceed?
Is that?
Yeah, that makes sense.
Accurate? Yeah.
Yeah. Just one small
no, but even if you see, if it is the splitting strategy used by node merging abstraction, the original paper, it concentrates only on one layer at a time. I don't know if there are extensions to that work that considers merging nodes across layer or not. If there is, other than this work that you're presenting. But if there it would be limited to exponential in the number of nodes in a particular layer. But if anything that considers across merging across layer, then it would be like what Kathakali said, correct? So it would be subsets of the nodes across the entire network.
Yeah.
That's the point that I guess Kathakali you were making.
Yeah. Yes, sir. That's what I'm trying to say.
Just one small question that I have is that see, here when we have this exponential set space, there's many different such partitions we can choose, and all of them will, if you follow Guy-Katz's method, will give us some abstract network by doing this min-max and sum, right?
Yes.
So in this case, for this example, at least for this property of upper bound 2, no matter what partitioning we choose, we will not get the.
We will not reach.
We will not be able to. Yeah. So okay, good. So basically, what you're saying is that the search space is exponential, and it may not also have the optimal thing in it. I mean, because it's exponential, it's hard to search through, but it also may not have the optimal thing.
Yeah. Yes.
No, but there was another related. Okay, yes. I mean, I understand. Another related question is, why do you say, in what sense is that network that you're showing is optimal? I mean, obviously, it's property dependent, I presume. But why? In what sense is it it's the most optimal? I mean, you didn't use the term most. So why is that optimal? In what sense?
So this the abstracted neural network, I'm saying optimal. I will come up with gradually I will proceed, and why I'm using the term optimal will make more sense. But at least for now, this abstracted neural network satisfies the property that if for all input between 0 and 1, the output will be less than 2, and this satisfies the property. And so we can say, so this is an abstracted network of the original one. So that's why we can say okay, this neural network exists, but we cannot may not come up with it by merging technique, but this neural network exists, and this is one such neural network.
But that is not the criteria of optimality. You're saying something like there is no smaller or something like that in some sense of.
I will explain as I go to the gradient descent technique. I will explain why I mentioned optimal.
Fine. So that criteria of what optimality is, I would look forward to that. Yeah.
So the limitation of merge-unmerge based abstraction is that this is restricted to local alteration. Okay, so given one input point, when you feed it to the neural network, and that result might result in a spurious counter example. If that results in a spurious counter example, and depending on that, we will do the unmerging or unmerging, and whatever the heuristics we have seen so far, they only concerned about the relation in a particular layer, whether the difference in the weight or whatever heuristics we have seen so far. So it is restricted to the local in a very small layer, or the relation between two layers or the particular layer, and so it gives a very local point of view. It doesn't show us, or it doesn't reflect in any form what happens in overall. It might happen that a neuron which have two neurons which might have very different values, but results has similar effect ultimately in the later layers. So by so as they have the similar effect in the later layers, they should be abstracted together. But it might not happen since the value in this layer varies vastly. So the local approach is the one of the greatest limitation of the merging and merging technique. So we will see, and yeah, that's what I said. They cannot discover abstraction requiring global reparameterizations. What does that mean? We will proceed and we will see. So this paper suggests gradient driven abstraction. First step is differentiable parameterization, and the second step is gradient optimization. So what is the idea? So idea is ultimately we make some choices, right? Which to merge, which to unmerge, and which concrete node of the actual neural network will be retained, or which concrete nodes will be merged to form abstracted node. All these are the choices we make. And so here the key idea is to come up with a continuous, almost everywhere differentiable parameterized abstract network, that's this one, where theta encodes the choices we make. So and like varying the value of theta continuously, we will create a continuous change in the behavior as of the network as a function. And by using gradient descent, we will optimize that theta, the choices we are making, and to get the best abstraction. And that's why and the neural network I showed earlier follows this, and that's why I use the term optimally abstracted neural network, because using gradient descent, we will optimize the choice of theta. The theta is the encoding of all the choices, and we will optimize the choice. And this works exactly like how a DNN is trained. So we will feed, when we train a DNN, what happens is we feed the input, there is forward propagation, and then we calculate the loss function, and the loss function, and by gradient descent and backward propagation, we keep altering the learnable parameters, the weights and biases. And this will act very similarly here. So we want to optimize the theta. So theta is the function of the loss function and the neural network, and this is the loss function. So the gradient is
one question. So what do you mean by fidelity here? You mean accuracy? Fidelity
accuracy
measured
irrespective of the
exactly.
property we have already mentioned before.
Yeah, the accuracy with respect to the property, or accuracy in the way, I mean, of the network itself, because there is a notion of accuracy when you train network.
Yeah, no. In
That's
this
the
case,
kind of accuracy that you're looking about, or the accuracy relative to this property?
Related to this property, not like we want to mimic the behavior of the network. It is not the fact. We are talking about accuracy with respect to the property that this network should satisfy.
Yeah, but that means that is where your question of optimality comes. Okay, so which means that this will be accuracy means it won't. Yeah, accuracy with respect to the property has to be carefully defined, which means that this will not falsify any looser abstraction to this, okay, will not that is derived in this case will falsify the property, okay, because this has to be carefully defined. Okay. There's a little bit of ambiguity there, what it means for it to be it's accurate with respect to the property. Okay, so which means, I guess so, what you're saying is that it will not, there is no spurious example with respect to the property. That's what you're guaranteeing. Yeah?
Yeah.
Okay.
So this is the pipeline. So given there will be the neural network that we want to from which we want to get the abstraction, that is n, and then we will define n dash this neural network, and by gradient descent we will find an optimized theta star, that is the choices we have made, and this will give us the optimal neural network, and from there we will get the ultimately the n dash, and we will see how we get the n dash with respect to the toy example we have taken. So when we do this gradient descent part, it will take like a training of a DNN. It will include the loss function, and this loss function is based on the defined on the property that we want to validate. And so after we get this n dash, we'll fit them to the solver. So either it can come up with a real counter example or the property is proved, or if it comes up with a spurious counter example, and then the spurious counter example will be added to the set of the inputs we have fed for the to come up with this optimal theta star. I will explain this in more detail as I go forward.
Yeah, but one question that I have there, which even if not now, I want to an answer is, so you hear the way that you've shown the flow chart, you always get either proved or counter example. Why should that be the case? Okay, is my question. Can it not end up saying, oh, I'm not able to, okay? I'm not able to find such an end star. That is not possible. That outcome is not possible by this method.
So when I'm saying it is this is the output of the solver, not like the how we are abstracting or the process, the algorithm of abstraction. I'm saying the counter example or proof is the output of the solver, and when the solver gives a spurious counter example, and that I will add to the set of all the inputs which were used to come up with this.
So the further refinement
Yeah.
process is not here.
So like I will explain this more as I go forward. Maybe
the refinement process is not here. Okay.
Maybe that will make more sense if I.
Fine. Yeah.
So overview is that we have already done the splitting depending on whether it's an increasing node or a decreasing node. So the abstraction process will have 3 stages. One is the copying and multiplying. Then there will be alpha multiplication, sound replacement by abstract nodes, and finally relaxed soundness condition for gradient descent. We will see as we will go in detail of each of the process. So suppose like we have this budget, like each layer should have k abstract nodes. So for each concrete node Ci, we'll create a copy Cij for each abstract node Aj, and we will multiply the output of them with the learnable parameter, that is lambda ij, the belonging from within the range of 0 to 1, such that summation of the lambda ij is equals to 1. So we need to make sure that the summation of lambda ij is equals to 1, so that ultimately the behavior of the neural network doesn't change yet. Yet we are not changing. It is exactly mimicking the original network. I'm not changing anything, because the output is like a fraction. When we are like splitting the nodes, like we're making copy of them and their output, and when we sum the output of all the copies, that will give exactly the output of previous, like the original neural network. And why we are doing this, I have already mentioned previously, like 2 concrete nodes which contribute to like similar values in some later layers might vastly different in this, like in the local view it might vastly different in the scales. So like to avoid this issue or to counter this issue, we are doing this step of copying and multiplying. Next I will go to the sorry. Okay. I'm sorry. I made a mistake. So why we do this copying and multiplying is, what happens? It might happen that one abstracted neural network is one abstracted node is responsible for multiple concrete nodes, or vice versa. Or it can happen in the like in an abstracted neural network that actually validates the property. It might happen that one abstracted multiple concrete node is responsible for one abstracted node, or multiple abstracted node is responsible for one concrete node. So to deal with this, we're copying and multiplying that for each concrete node Ci, we'll create a copy Cij for each abstract node Aij.
Can you explain it in terms of example? I was not completely clear about this budget K. Is it this? Yeah.
Okay. K is the, suppose we have 50 layers. Sorry, 50
Suppose you
neurons.
had K is equal to 4. Okay.
So we want
And
4 neurons per layer. Okay, and so I'm
no,
just
for every layer, it can
every layer.
have you can only keep 4 neurons. One abstract node can represent 4 neurons per layer, but which layer? I
Okay,
mean,
wait, no,
layer
no.
across all layers or what?
Okay, I'm saying ki, what happened? What I'm saying is K abstract nodes per layer. I'm just giving like the definition why I'm writing K over here. Like in the abstracted network, in every layer I want K nodes, and but in the original network there will be like more nodes than K. So it might happen in the abstracted network, which actually validates the property. It might happen that one abstract network might be responsible, one abstract node is might be responsible for multiple concrete node of the original neural network in one layer. In that layer, one abstract node might be responsible for multiple concrete node of the original network. Also, it might happen that multiple abstract nodes share the responsibility of one node in the original neural network. That's what I'm saying. Like, does it make sense? Like, So what we have done here is like we are making copy, and after making the copy, we are multiplying by lambda ij. So we have made in the original network there was C1, C2, and C0. We have made 2 copies of C0, C01, C00, and we have multiplied by 0.5, 0.5 over here, like 0.5, 0.5 adds up to 1. Now we will go to the next stage, alpha multiplication. So what we do is
how you choose the abstract nodes you still haven't described.
Okay.
Yeah.
Well, we are not choosing lambda ij.
But you do say for each concrete node CI it creates so many copies.
It
where
creates
J, but we don't even know what the J is here. Okay.
like okay. So
In
for
all the abstract nodes, in Guy Katz's approach, you know that there is at most, I mean, if you merge everything, it will be 1, or you can, and some combination of that, because here you say that abstract nodes can
okay.
cross
Okay.
layers, but how do you choose how many abstract nodes? Do you choose ahead of time, or you kind of, similar to saturation strategy, there is some strategy that you have to construct the abstract nodes?
I'm sorry, I do not understand.
A simple question. How do you decide what the abstract nodes are? I mean, what concrete nodes make into one abstract node?
I'm not saying that we know what concrete nodes will give which abstract node, but the example I'm giving 0.5 or 0. Multiplying them, and that thing is like this will eventually through gradient descent we will know which parameter what are the parameters.
So no. The reason that I'm getting confused because is the number K abstract nodes per layer. Okay. So that will give this is exactly K. So this will give the number of abstract nodes also. So because it is K abstract nodes per layer, and since the original network has a fixed number of layers,
fixed number
you
of
know how many abstract nodes.
Nodes. Yes,
Now I get an idea. Yeah. Okay. Yeah.
Okay. So next I will go to the alpha multiplication. So what we do here is I previously mentioned also how we are not very sure
Yeah.
about.
So once again, sorry, that K is given. Is it a hyperparameter that is also determined by your gradient descent method, or
No, it is not
budget
determined by gradient descent method.
It is
No.
not, or it is?
It is not.
Okay, but that is not a hyperparameter.
No, it is not.
Yeah, within that, what concrete nodes can go into forming your abstract, etc. That is what the gradient Descent determinants.
That
Okay.
is the parameter over here. Right,
Okay.
right, exactly. So now we will multiply the input weight by some alpha, and if we scale up the input weight by alpha, and then we will scale down the input weight by alpha, or vice versa. So because we know that for all x, this is true. For all x, we know that for all x, this thing is true. So it doesn't, still there is no over approximation has been introduced or anything. It's the network still is exactly like there is like there's still no over approximation introduced, and the output is still will be same. So now we will do the sound replacement by abstract nodes. So we will replace Cij, that we made that copies, right? We will replace Cij with weights Wi by the abstract nodes Aij with weights W dash J. And it should, we should do like but it should maintain this property that ReLU of Wj dash should be greater than this. If for the increasing in the example we have taken all the nodes as increasing nodes, so for the increasing nodes this should be satisfied, and for the decreasing nodes the vice versa, that Wj dash ReLU of this should be less than equals to ReLU of the original x into Wi. So, and for all x belongs to I is a set of inputs. So I is obtained via interval propagation, and that we can, because of the monotonicity property of the increasing decreasing splitting of the network, we will get that. And this Wj dash, how we will determine this Wj dash will come up, we'll get this Wj dash by the gradient descent process. That we will see. So what happens is ultimately, like previously, like when we made this alpha, like we multiplication by the alpha, here it is alpha equals to 2 for this neural network. So this is -1. It was previously -2, now it has been -1, and we have multiplied the output by 2. And in this case, like after the gradient descent and after the entire process, and we will finally see that the weights got replaced over here 0.5, 0.5, and also 0.5, 0.5. Previously these were different. So this, what the W dash J will be, that will be determined by the gradient descent process. So here the learnable parameters are lambda ij and alpha and Wij. These are the learnable parameters, and our target is to get the optimized value for this. So also, why when I was saying one of the important issue with the merging and merging technique, that it always look at the local pictures, and also like the search space of merging and merging technique was smaller, but this also, the search space of this technique also includes the merging and merging search space, because we see if lambda ij is either 0 or 1, then it is it's exactly like merging, either it is getting merged or not merged. If alpha, we take alpha, we are multiplying the weight, scaling the weight, right? So if I do not do that, then it still remains same. And if it happens that the optimal Wij happens to be one of the min max heuristic depending weights we got in the other, like merging and merging technique, that will also be included in this process. So now what we will do is the relaxed soundness condition. The original condition, which I already showed over here in this slide, that is the S, this condition. So why we the original condition S is hard to enforce with gradient descent, because like gradient descent is like we are using the gradient descent to optimize the other parameters. We are not like for infinitely many points, we are not like this. We need to also make sure that this holds, the property S holds. So instead of that, we will have a relaxed condition. So the relaxed condition is, we are like this there is some part like we are adding this delta ij to this, and how we will get the delta ij? Delta L is the maximum of this difference of them. So maximizing the difference of them, we will have this one factor delta ij to relax the soundness condition. In ideal case, delta ij should be 0, and this like the S to be S, so and then it becomes S eventually. But also in the practical case, there are non-zero residuals, which also is sounds abstraction. In this the toy network we have already showed over there. In this case, the residuals are 0, and so the producer, ultimately the abstracted neural which was like ultimately we got, that will produce a plot which is very equivalent to the green plot shown previously. So now counterexample driven loss function. So our goal is to find like an n dash which is strong enough to prove the property P. So this is the loss function here we are defining. And
Yeah, Kathakali.
yes,
I mean,
sir.
in your this thing, there are some palettes. Okay, can you remove them because they come on? See, I think it is coming. There is this that you could do, and then there is also this participants pane. Okay, which comes in the way of.
Oh, so I don't think I can get rid of it.
Yeah, please get
I,
rid of it so that.
I cannot get rid of this
But can you move it
participant.
as far to the right? I think there is a way to minimum.
Oh, sorry.
Okay, you can. Yeah, okay,
Sorry.
fine. Yeah,
I didn't notice before.
thank you.
So this is the loss function. This is how we are defining the loss function, and this is like this loss function. We are doing it over an estimated by a uniform sampling.
Can you go back to previous slide because of that thing that I was not able to exactly understand what delta is? Okay, so relaxed. This is the condition that you preserve. Huh? This was.
The original condition S was, I'll go back to that. This was X. This is the original condition we had.
Okay. So that and that is being replaced by
this relaxed condition. Can I proceed?
Yeah.
So now we will go to the counterexample driven loss function. So what happens here is like it takes an uniform sampling. This is the uniform sampling, and on it will perform the gradient descent, and we will get a loss function. That is, this is the loss function we will get. And depending on the loss function, it will then change the parameters, update the values of the parameters, and exactly how like DNN is trained. But how is this important over here? Because this gets rid of the two notion of locality I previously mentioned. That what happens is, in this case, at every step, there will be changes across all the layers. But previously, when there was in every step, there was only change in the one layer. And so the change was local. Also, it was depending on only one point, one input, single input point. But in this case, we are doing it on a sample. That is I, that is denoted by I over here. And in every step, whatever the change you're happening, that is happening across all the layers. The small changes are happening across all the layers. So now it is giving us whatever the change is happening for each step, the change is global. So it is not restricted to a view of the very small region of the neural network. Now the training and abstraction is that we will by the gradient descent process we will get the optimized theta. And finally, we will extract n dash, that we will keep the abstract node Cj with the new with all the incoming weights previously there, but we'll scaling the output weights by lambda ij, summation of lambda ij. And the resulting neural network is equivalent to the trained by gradient descent method we call the trained network. This will be resulting, and now this will have fewer nodes because there will be k part layer nodes, and hence it will be easier to verify because again we were dealing with the scalability issue of neural network. So what happens is, this is where we were at the last in the example that I was showing, and ultimately this two will merge, and this two will give rise to A1, and this two will merge, and this two will give rise to A0. So the choices which were encoded got optimized by gradient descent algorithm. So that's why when I was mentioning the abstracted network was optimal abstracted network, I meant optimal by optimum by this notion I was meaning it. So the gradient descent benefit
optimal with respect to that loss function that you
loss
have.
function that it was defined. Yes. So the benefits of gradient descent is so it gives it like the Sigurd or the Sigurd based approaches were restricted to the local view of the network, but in this case it like the global non-linear dependencies are also taken care of. Gradient and this coordinates change across the layers, balance multiple objectives like we have different parameters, and discovering the non-obvious abstraction. The non-obvious abstraction is that abstraction which were not possible to reach by merging and unmerging technique, and this is very much similar to the standard training of
But
the
there is one thing, I don't know if I missed that detail in your thing. How is which nodes to merge across layers pick? How is that determined? Because that can potentially result in a blow up, no? Because there are so many combinations. Even though you fix the number of k fixes the number of nodes per layer, there is a lot of freedom in which ones you choose across the layers to merge and so on, no? Or you don't allow that? You do, no? Yeah, this method does allow you to merge across layers, correct?
Yeah. So
But how do you choose? How do you?
Yeah, what happened is we are making the summation. Ultimately,
correct. Yeah.
Ultimately we have k nodes in one layer, right? And so what we are keeping the input weight as it was, and but the output weight is the scaling the output weights by this, the summation of this thing. So what happens is this is between the range of 0, 1, right? So from multiple nodes of previous from not previous, I mean the original network, the concrete nodes, a fraction of the concrete nodes are getting the effect is getting into the new network we have got, but there is no blow up because we have already fixed the that's what I was
clever. Okay.
Okay. So okay, now the summary is the let's summarize the entire
Yeah,
thing.
but did you describe the previous slide? You had
Yeah, I just went through.
No, the one before that.
Oh, this one.
That's the same thing. Okay, fine.
That was the example, after extraction, how it looks. Okay. So finally, okay, I'm summaries. Let me summarize. What happened is that we are abstracting a neural network, and the abstraction process is gradient-based optimization, and then we will verify that abstracted neural network, and to get whether there is to come up with a spurious counterexample if there is, and that will be fed back to the sample. When I was saying this loss function, I'll just go back once more. So what happens is that suppose by uniform sampling from I, suppose such a sample is S. Okay, so when we get a spurious counterexample, we will add that point into S, and then again we will repeat the process. So that's how it is counterexample driven loss function. So but every step, if we get this is a counterexample, suppose, and this will get added to is the sample on which we are like doing this, so that what happens in the next step, the effect of it gets like included while we are changing the parameters. So that's what I was going to okay. And that's all over here. Now the experimental setup is that the MNIST database has been taken, and it has in the original neural network it has three hidden layers with 50 neurons in each layer. And our budget was to abstract get an abstracted neural network with 30 neurons in each layer. And for the comparison, we will run the Seeger technique until we get and the budget of 30 abstract neurons per layer, and then we will stop, and that will be our comparison for like that will be the base of comparison. So when we can compare, we see that in all the cases the loss is lower than the Seeger loss, and as the loss is if the loss is lower, then it is better for our
But
like
how do you compute the Seeger loss?
it's the same method that was defined in the paper in the
So you take the network that you get from the Seeger and then you apply the Seeger loss,
yeah
Seeger loss.
yeah
Uh,
right.
uh,
And so over here the key advantages is that
No, but
it's
the real thing is loss is fine, but on real properties in your experimental section, there wasn't anything to show how many, like actual performance, how many it did
um,
verify, how many did not, and so on, and how many
so for
I
these are the instance property instances, and with respect to that we have performed like whether in Sigurd what is the loss, and in this gradient descent based technique what is the loss, and like I don't I mean what's the question, I'm not that's not
The
clear.
question is usually they show how many properties the original network, I mean, abstraction technique was able to verify, how many this was verified, what was the, number of refinement steps, and those kinds of things. Okay, this is,
But this the paper is restricted like to
I see.
this
So,
this is
so the paper does not have
no.
experiments outside of that thing, is it? Yeah.
Yeah. So we will see the key advantages of our approach is that it maintains the like formal guarantee and works for unbounded data sets and incorporates global behavioral informations that I have already explained before, and it also avoids the suboptimal margins like the which and so efficient verification is there, and the abstraction process is automated, not not the refinement is not heuristic based, and so it is compatible with the existing verification tools and works for any property reducible to output bounds for a given input range. And so the unique benefit is the gradient descent enables the property preserving search over the abstraction space. And the conclusion and the future work is contribution is parameterized DNA abstraction via differentiable encoding. Gradient-based optimization outperforms the Sigurd heuristics that was shown before. And future direction develop into robust verification tool, extend the property preserving comparison and for larger, because this is a very small neural network that was considered, so for the larger scale
So
evaluation.
extending to property preserving compression, what does that mean? That is something similar to what the Gaikatz people did, that Pranika talked about,
Yeah.
having some reduction, property guided, I mean, sensitive reductions. Huh?
Mhm.
Okay.
Yeah, that is my presentation. Thank you.
Yeah, I have exhausted my questions. I mean, if I can think of any, Diganta, you have any specific questions to her? Diganta? You here? Diganta?
Okay, I will stop sharing, and if he has questions, then I will reshare and
No, but
answer them.
yeah, I mean, he's able to hear us. He's not responding.
I don't know, like he
Oh, he's
hasn't.
muted.
Mm.
Hi, Diganta. Hmm.
Should I stop sharing, or like should I wait?
No, that doesn't matter. Okay. No, let him. You mean. I don't know why he's not responding.
Go ahead. Hello.
Student.
Hello.
10%. Diganta, I was asking if I've exhausted all the questions that if you have any questions specifically you want to ask.
No. I think I don't have any questions. I mean, so just one small thing that I wanted to maybe say. I don't know if this was clear or not, but this you had asked a question earlier that okay, what is it that in this example, what is it that this technique does that GaiCats does not do, right?
Oh, no. I mean, there are several things that came across. Okay, my question was not as general as that. No, in this, I could understand there were lots of things that it does differently. Okay.
Yeah. I just wanted to make sure
I
that
think
that
my
was sure.
question was twofold. One was the optimality question. Now that has been answered. Okay.
Yeah.
But in the experimental section question, yeah, I didn't, why, there was only comparison of some loss factor. Okay. But there was no comparison on like most on I mean, you take the same thing, you apply for verifying the same properties, how long it took, and those kinds of performance comparison was not there.
I mean, that is the downside of the paper itself. I mean, that is so. Yeah. Um.
So such a comparison was not done.
Yeah. So the reason was
That's
twofold.
what
I mean,
Kathakali
yeah.
did answer. I mean, Kathakali answered all my questions that I asked her properly. So there was no.
Yeah. So I mean, my point with respect to bringing this is up, I think Kathakali has answered everything perfectly. Like I wanted to maybe initiate some discussion because this is some work that I was a bit involved in, so I thought that maybe I'll address this question as a general level. But yeah, I mean, generally speaking, what happened was, see, I mean, this one of the things that we wanted to kind of do was, without even knowing whether or not this particular property holds, even if we let's say that we have a network for which the property does not hold, even then this loss, if we can reduce the expectation of finding a counterexample, then it will still kind of you know get us to a network where at least the chance of getting a spurious counterexample will be lesser, right? So in that sense, this loss will be sort of a unified view onto whether or not for this particular network.
That I understand.
Uh,
Yeah. But
yeah.
where I did not get, I mean, Kathakali, I mean, maybe you can answer that first, and then I mean, if I still have question, maybe Nilendra can. I asked you a question about refinement, how that happens. I'm not sure if I got a full answer for that. Okay.
Okay.
Now, how often do you have to run gradient descent? You run gradient descent, get one solution for theta. Okay. I think you did mention after that you check the property, and then you said that you take the counterexample and then you add it. Okay.
I add it to
Or
the
the
sample set.
negation of it or something like that, huh?
And then again we do the
Yeah,
same
but
step
when you
again.
say you add that the negation as to your that you showed the ReLU, I mean the constraint.
No, okay, no. When we get a spurious counterexample, so for some x, that there is a spurious counterexample, right? So we will add that x to the input, like to the input sample.
Okay. But do you do that? Doing that one at a time is too expensive, no? I mean, is there some method discussed in the paper, which you did not mention in your talk, that somehow gets a whole bunch of counterexamples that can be eliminated, spurious counterexamples that can be eliminated simultaneously? Or did not?
Maybe I missed it. I don't know. I mean,
No, I mean, to answer this, no, actually, we didn't. We talk about this one at a time thing itself in the paper because what you're saying is right. Ideally, we should want to eliminate a bunch of spurious counterexample by adding maybe a class or a large number of spurious counterexample to S. But what we have done so far is just this one at a time kind of a thing. Yeah, at least right now that's what we have explored. But I think, I mean, that should be doable in the sense that all of the details of how you actually do the merge should remain the same. It's just that now we'll have to have some method of getting a class of counterexamples from this single one. So the generalization needs to happen somehow. But once that's done, that should be doable. But yeah, we didn't discuss it in the paper.
Yeah, I mean, my questions are kind of address both your thing, okay, to Kathakali, I mean, to test how well she understood the paper and so on, and what is in the paper as a future kind of a thing. Something related to that was, see, the reason that I asked about the performance on the thing, I mean, that would be interesting to do because one of the complaints that original Gaikatsu's work had was, okay, most of the times it kind of, after a few iterations, it just collapses, I mean, or reverse collapse to the original network, okay? Here in the refinement process, does it look at, different combinations and then come up with something smaller to prove it? I guess because unless you do those actual experiments on examples, you won't know, no?
okay.
That is the question. If there was some comment in the paper with respect to that, first to you.
If I whatever I understood from the paper, it says that in the merging and unmerging technique, we fall back to the original network because we either go from we merge some nodes to get the abstracted network, and then we do the refinement process and we keep unmerging. But in this case, this is not happening. In this case, in this case, there is no merging or unmerging. So we already know, so for we have already said that there will be k amount of neurons per layer. So it might happen the abstracted neural network.
But why do you say that? Once you get a spurious counterexample you add, then the next time when you do it, it can come up with a different kind of merging.
Yeah, because so here it is actually so we have this parameters, right? We have this lambda. Okay, I'll just let me go back to my slide once more. Yeah, we have this lambda ij. So we said that lambda ij, what is this doing? It is within the range of this is within the range of 0 to 1. So what was and this lambda ij get it ultimately we get an optimized lambda ij for each of the concrete node to the abstract, the copy we had made. Like for
yeah, I think you did answer that.
huh.
So there is really
So there is no unmerging thing happening. So it might happen like for some of them that is 0. So for one
that's fine.
abstract,
So that answered part of my question. So if you did have a refinement thing, so you need to run one gradient descent per refinement per counter example in this case, correct?
Yes, correct.
Yeah, and then it will come up with a different set of parameters.
Yes.
Which will have some kind of an equivalent of a more abstract network, which is not strictly constructed here. That's what you mean when you say there is no unmerging and merging happening explicitly, correct?
Yes, exactly.
Okay.
That's what I meant.
Yeah, is that correct, Digant?
Yeah, that I think is exactly what's happening. I mean, yeah.
Yeah, that makes sense because it's more semantic abstraction. Why do you want to really explicitly
force some structure or something with it?
Yeah, so I understood. Yes, that's good. So I guess then this is a question that I don't know if Kathakali can answer. So what does future hold for this line of work? What does the paper say, Kathakali? Maybe what you can say, what I think what the paper says. I know that you had the future kind of a thing.
So I'll go back to that slide. So it says that develop this abstraction technique into a robust.
Larger scale evaluation. That is the most important thing.
That's the most important thing. Yes, the larger scale evaluation because it is done in comparatively smaller neural network.
What do they mean by convert into a robust verification tool?
I mean, okay. What do you? I don't know how to explain.
So, firstly, I mean, do you feel that is adequately answered in the paper, or do you think that the paper is not? That's if you think that we are not, you can say that it's like it's not mentioned or something.
Diganta may be an author on the paper, but he's donning a different hat today.
Yeah, definitely. Because I mean, see, this is like if you think that this is something that was not there in the paper, it's not there, right?
Yeah, I mean, so the paper says that this is a prototype. Am I audible? The paper says that this is a prototype, and this prototype, like the future work to be implement this prototype into some robust tool that will like eventually give us. That's what the paper says.
Yes, they're very much prototype. They don't know how. The robustness means that there is too much. It's not stable. I mean, there is something that small fluctuations might result in.
So actually, I mean, perhaps I can. Yeah, go on.
But I just like noticed this thing like when we have increased this from like this is the 80080040031, it was like pretty close. These two are pretty close. But in other cases when the epsilon was less and there was a significant difference, but this time is like quite close. There's one thing I like noticed but not particularly addressed in the paper.
No. Okay, this brings to the thing.
Good point.
Attention, Kathakali. I mean, maybe you should answer because we do have time. What is epsilon here? And first you decreased and then you increased.
Okay,
there was not a corresponding, direction. What exactly is epsilon? That is, I didn't pay attention to the original thing. Can you elaborate? What is epsilon and why is this not going in a monotonic way? Okay.
I do not. I cannot answer why it's not going in a monotonic way.
No. First answer what is epsilon?
Okay, what is epsilon is the like it is like the small changes, right? I mean, this is the perturbation of epsilon is the measure of it, like how much it is changing, like
You know,
The
it is for the property or it is for something
no,
like
I think it is on the input, the instances, okay, I'm like, given one property, and like over here, the like instance is like the property, right? Like, in one case, it can be greater than 4 and greater than 2, like that kind of thing. I believe that is the
the
case.
robustness properties
Hmm.
have an epsilon parameter. Okay.
Hmm.
If you're
I,
disturbing the inputs within a certain tolerant level,
that's what I understood
that's what this epsilon
from the
is.
paper.
Okay.
Uh, yeah.
Not any of the parameter like K or anything. No, the K is all the K that was used here was fixed. What was the K that was used here for the
The
company?
the K I already mentioned was the budget of like
No,
per layer, how
in
many.
actual experiment for calculating these numbers, they must have fixed a particular K, no?
Oh yeah, that was there. I mentioned it. It was
Oh,
30 abstract neuron. There was
okay.
40% reduction.
Okay, did I say? So these were comparison for those epsilon numbers. So you don't know why when you increased, okay, let's see. So when you go down 0.8 to 0.4, much a tighter, stronger robustness property, you were able to get, or even in the original one for then when you increased it, yeah, that is correct. It's monotonic. I mean, from you reduced it way a lot and then you increased it. But the question is, this increase that you got for the third case was much larger than 0.08, but you still got a reduction.
Mm.
Yeah, that is what is a bit puzzling, no?
I noticed it, but I do not know. I mean, the paper doesn't explain it.
Yeah, I mean, so I think Kathakali said all the things accurately with respect to what's there in the paper. What maybe I can say now, as one of the people involved here, is that see, we don't really know why this sort of a like pattern is appearing in the table. What we imagine is this is perhaps a reflection of how hard these epsilon robustness properties for these particular instances are, in the sense that if this is an easy enough instance, then there exists a network out there for this particular budget of K, which will achieve a low enough loss. Whereas if this is actually a hard instance, which is the case for a large epsilon value, right? So if the epsilon is large, it's unlikely that exists abstraction that is good enough to prove the property, which means that we would expect, on the other hand, the loss to be somewhat bigger, right? So that is partially perhaps explaining this, but I think all the kind of trends that we're looking at here, it's not very clear why they're happening. Yeah, and more experiments is definitely needed.
One more question, Kathakali, for you, and first, and then Diganta wants to go to the previous slide.
Okay.
Now, K, the budget, the way it is defined, I can understand. It's a simple way of doing it. It gives the. Why is there no parameter, since it is using this K to also potentially, I guess you cannot, there is no, I guess there is no parameter. I mean, you could presumably, just like this K, can you not have some parameter, either hyper or non-hyper? Okay, probably something, if it is non-hyper, it has to be translated somehow into the theta, one of the theta parameters that can indicate which nodes, what layer you want to either dominate, which nodes from which layer, or is it not? I mean, and then can you encode your loss function somehow in terms of those things, how far those layers are from the output or something? Why is there no parameter? I mean, the two questions, does the paper address that? Okay. The other thing, the other thing about the choice of the thing. Now, I know that is indirectly done using this alpha parameter, as you explained. I kind of asked this question already, okay, and you said that that is determined by some alpha, okay, and then during gradient descent, it kind of determines that. So there's no control over it right now. My question is, does it even, as future work, does it even make sense to have some control over it, introduce some control over it by introducing either in the loss function encoding or other ways? I don't know how. Some parameter with respect to what nodes from different layers that you want to choose or how many and so on. So the question to you, Kathakali, is if they even address this in the paper or not.
Okay, so okay, if I understood the question correctly, you're asking that whether do we have any control over like which node will get the responsibility of
No, I'm
original.
not saying control to such a fine control. You have K, they fixed K.
Yes.
Why
we
not
have-
say have another parameter? Oh, these many nodes from this layer, that many nodes from the other layer.
Oh, okay. I
Why
got
didn't
it.
they do that? Why didn't they do that? Even if they did not want to incorporate that into they could have chosen so many, etc., and then done some way of encoding that in the loss function.
Mhm.
Was
I
that?
understand. I understand your
Mm.
question now. But like the paper doesn't talk about it. It also doesn't say why we have like. But I guess that there is like restricting. Maybe it is like a restricting particular K. At least ensures that the abstracted network will smaller in size. I think that can be one of the motivation, but
Yes.
I'm not sure why
That I
exactly.
understand. So, but the other one that I'm talking about can give you more optimal or more precise things. Okay.
So across the layer, the value of K can be different. That's what you are asking, I guess.
I mean, I'm saying that they can also reduce and they can give variation over precision. Huh?
I understood the question, but the paper doesn't talk about it, and
I don't even know how to do that. Okay.
I also haven't thought or paper doesn't talk about it.
Yeah.
Maybe Tiganta can like.
Yeah, I think what the guess that you have is kind of on to what the reason was for this particular test. We actually tried experimenting with the other a version of a different parameterization where K was also free, right? And what that basically looked like was that instead of saying that sum of lambda should be equal to 1, we'll say that sum of lambda should be less than equal to 1. Correct? So basically, I mean, so in the sense that each concrete node should go to exactly one abstract node, but then there can be multiple abstract nodes which don't get any contribution from any concrete
There's
node.
already
And then
some
later on,
parameter there that does give you some.
yeah, exactly. So this can happen even with this particular K. It can happen with the network that we get.
Yeah, but the choice don't have direct control, but it chooses itself. No?
Yes. So it can happen that in the network, that even though you have given a budget of 30 neurons per layer, only 20 of them are really active according to the lambda values, right? But what we found experimentally is that, see, typically this optimum happens for a value of lambda which is not 0 or 1. That is often the actual optimum, and that is also often what gradient descent returns. So we don't get to see this in the experiment. So if we give a budget of 30, the optimization process ends up using up the whole budget, right? So it's very hard to kind of define the optimization problem in a way where by adding some additional terms to the loss function or something like that, like something like a regularization term or something like that, where the optimum will actually be forced to consider, how many non-zero values of lambda should I have and so on, right? That tends to create these competing motives, and then the optimization problem sort of decides to choose something that kind of does the best it can for both, but doesn't really optimize for either. So experimentally, in our early experiments, we found that was just not going to work, and therefore we thought that, okay, let's just make sure that we at least whatever we deliver, we always ensure that the budget is going to be satisfied.
Yeah, okay. I got it. Yeah.
So it's kind of like we want that budget to be a hard constraint as opposed to a soft constraint, right? So all the other things, I mean, in terms of decision and everything, we can choose it to be a soft constraint, and the budget we want it to be a hard constraint. So I think what maybe one of those two things need to be a hard constraint. If both of them are soft constraints, then the optimization problem just comes up with a very weak, I mean, not a particularly useful
Correct. Yeah.
Pareto
I think
optimal
it's
network,
better
right?
that that you can have it at a non hyperparameter thing, and the designer has some intuition as to what the various layers are meant to do or something like that, and then it's better that k parameter is defined more in a more refined way, with the intuition about what the network is. Like, for example, if indeed digit recognition, the first one recognizes broad strokes, and then second layer somewhere
Right.
recognize a small thing, then you could do something, no?
Yeah, exactly. I mean that is the second part of your question. I think that is true. I mean we can choose different k for different layers. What the heuristic actually we choose is that we fix the percentage in every layer. So if the layer sizes themselves reduce, we kind of fix the percentage. But yeah, I mean there might be a better way to do this. But then yeah, I mean that becomes a hard space to search through, in the sense that okay, how many like what should the k for each layer be? And I think that's kind of related to the problem that we have when we train DNNs, where we have to choose how many neurons to allocate to each layer in the first place when training, like before training, right? When we choose the architecture. And I think that is also kind of an instantiation of a similar hyperparameter search problem. There is a lot of existing work on such kind of hyperparameter search, especially in the case of neural network architecture search. I think those might be relevant for solving this, but yeah, I think yeah, you're right in the sense that if we could somehow smartly choose k to be different from various different layers, we might get something more precise.
Another question I had was, did the paper, Kathakali, did they mention about how the sample size? Now, I know that is kind of should be part of an experiment. I don't know, it cannot be just showing the loss function. Okay, do they run it on actually MNIST data?
Yeah.
With large number of samples, I know this 3 by 50 MNIST classifier is there. That I understand. That fixes my question is about the data that is actually used, over which the gradient descent is run.
I don't think it's the paper says something. The paper exactly says whatever I have written over here. Exactly this. I don't think other than anything else, the paper says anything.
So what we do mention is just this much, that the data is uniformly sampled over this space of input values that the epsilon
But the
property
MNIST data doesn't guarantee such anything about the distribution of how
yes.
the sample, no? So did
yeah,
you?
and we don't want to follow them this distribution. The reason is, I mean, see, if you look at the loss function, or what we're trying to find is, what is the probability of us getting a counter example, right?
So then my question is even more relevant, okay? So which means that you did not use MNIST data, okay?
Right.
Data
It doesn't even make sense to use MNIST data, because, for instance, in this case, we're doing epsilon robustness, right? So all the input points need to be within an epsilon perturbation of particular specific input instance, right? So, almost nothing from the MNIST data set will satisfy that. So it doesn't, we cannot use MNIST data. There are not even enough samples. And also we don't want to use, because it doesn't represent, so the class that we're trying to capture is what happens if you do various random epsilon perturbations of a very specific.
I want Kathakali to kind of understand that. I mean, you understand the point that Digant is making, and the point of my question, no?
Yeah, I got it.
Yeah. Now, given that, then how did the paper so so the generation of the data itself, so the inputs, then there is question about how representative the sample is because you did it on your own, if the authors did it on their own, then that question becomes even more relevant. The size, the distribution, how exactly it was generated, etc. For that, being the author, so you
Yeah,
generate.
so maybe I'll take that.
Yeah.
Yeah, so I think so. What we do mention in the paper that we do a uniform sampling, and that the sample size is for this case of the order of 1,000, few thousand, right? So for this particular experiments, if I remember correctly, we took something around 2,000 samples.
But is 1,000 enough? What is the?
That's a very good question, right? So we don't know. Actually, I mean, the best way to determine whether the 1,000 is enough is to so there is a like to do some kind of hypothesis testing on the hypothesis that there is no actual counter example, right?
Yeah,
And
like
if
that
we do
adversarial attack paper did. Okay, they have a
exactly.
very strong basis of this hypothesis testing. Now, yeah.
Exactly. Yeah. So if one were to do something of that nature, then at least for given values of given degree of how happy we are with respect to our confidence on the probability estimate, we would get some probability estimate with respect to the number of samples that we have, right? The issue with that, of course, is that that can only be done once the gradient descent is completed, because so such hypothesis testing would basically be like, oh, you draw a sample, test, then update some counts, draw a sample, test, update some counts, and so on, right? And you keep doing that until and unless the probability given by these counts have enough confidence behind them that you're happy with those probabilities, right? This cannot be done within a gradient descent loop, but it is not feasibly, in the sense that now if to do this within a gradient descent loop, you'll have to for each iteration of the gradient descent loop, you have to run this whole sampling process, which will probably take way too long. I mean, already gradient descent itself is kind of expensive, right? So that I think for that reason we have to kind of fix a sample set from beforehand, and it is the case that there could be a chance of some sort of overfitting, and there could be a chance of because of overfitting getting spuriously low reading of the loss. The way that we avoid that is that every epoch of our gradient descent run, we kind of redraw the set of samples, so we don't keep reusing the same set of samples again and again, but we use one set of samples throughout an epoch and then redraw and then use another set of samples throughout an epoch and so on. And then finally the loss function that we see, before we test that loss function, we redraw the samples again. But yeah, if we don't have a confidence interval or anything on that loss, which is, I think, a good point here.
Yeah, okay. So it's 11:30. I think that's the hard stop. So what do we do with Maya? You're here. Can we just continue, or you want 12:30? I mean, I didn't.
We can continue, sir. Hello. Am I audible?
Yeah, you are audible.
Yeah,
so then continue. That's best. Okay, so let's continue and finish it off before lunch. Yeah, then we can.
Yeah, just a second. Give me.
So, by the way, Maya, any questions from your side, or?
No, I was about my presentation as well. Just
yeah.
It's just 1 second. I'll share screen. Is the slides up?
Yes.
Let's start.
Yeah, it's visible on my end as well.
Thanks. Yeah. So should I start?
Please.
Go ahead.
Yeah. Good morning, everyone. Today I'll be presenting this paper called L*LM, learning automata from examples using natural language therapy as part of my presentation. So this is the outline. I think I'll just move past it with my convenience. Yes. So the problem in
The
hand we
outline
have.
was very long. Can you let slide? Yeah, can you?
Sure. Yeah. So we'll be sorry. Yeah, I'll just go through it first. So we'll be discussing what problem we are trying to tackle here at large, and we'll be discussing L-star algorithms overview. We'll not go into the depth or the correctness of it. I think it. I thought about it, but I thought it will diverge the conversation towards L-star than L-star LM. And then we'll be looking at the example on which we're trying to understand how the experiment will work. And there will be two techniques, two components or two models. One is the LLM interaction, and the other is expert resolution. That's different. So these two components we'll be discussing that are important for the algorithm, and then how we incorporate these two is using the DIS algorithm, which is part of another paper in 2022. Uh, Although this is black boxed in this paper, I still tried to make sense of what is like. I still try to see how much I want. Like I looked up on the internet just how much of it, or also Diganta's previous interaction helped in understanding what this is as well. And then we look at L-star LM as a whole, and then experiments, observation, conclusion, and prediction.
Okay.
Sure. Go ahead.
Thank you.
Yeah. So the problem in hand we have right now is called DFA identification problem, which is a very fundamental problem that a lot of us have come across in a theory of computation class. In the first few classes itself, once you know the definition of what a deterministic finite automaton is, or we call it DFA, is what we are asked to do is like given an arbitrary specification or set of uh, given an arbitrary specification, how does one attempt to find an automata that describes or that uh, like that describes the specification? Like we'll just look at one example. A basic example that we have come across in classes is like construct a DFA that accepts all strings from the language, such that the length of the string or the size of the string is divisible by 3. It could be like the size of the string is even or odd or divisible by 3. So how does if you are to think about it, how does a student in the first few lectures itself, when they're not equipped with a lot of stuff, but just equipped with the definitions of what an automata is, and what the transitions are, what the states are, and what does the semantics of the states and transitions are. So if you think about how does a student approaches to construct an automata for, let's say, this language, like length of this string, like size of the string is divisible by 3, is one can think of, let's say the alphabets here is just a single letter A. So it could be the set of languages here could be like epsilon A cube A bar 6. That will be the language, that will be the positive examples. I'm using the word positive and negative examples because we'll be using those terms in the future slides. So how does one attempt to make an automata? If you're just to think about how does a human brain think about it, is we might start thinking about like, does an epsilon is first of all an epsilon accepted in the language? So if it is accepted in the language, we'll realize that okay, if the start state has to be the accepting state as well. So if we make the first like one state automata, and we make it accepting state as well, and then you realize that okay, does is the A accepted in the language, and we realize it's not. So the transition from A, the transition by A should go to a non-accepting state. So this is how like we tend to think. So how we approach this is by like instinctively we scramble and make a three-state automata with appropriate transitions, which would look like this. Like if you think about it, we started with one state and then we added, and we also, like if we look at it, we asked ourselves that is epsilon accepted by the language or by the specification, or A accepted or double A accepted. So we are also uh, like this. I'm just building platform for something that we will call as a membership query. And so when we ask the question that is epsilon accepted in the language, that is we will refer to it as a membership query for the automata. Like, is the alphabet is the word any word accepted in the language? If it is accepted, then like the it's a yeah. So if it is accepted, then the membership query is positive or like one. Uh, but then the question arises that how does one approach this problem
Hello?
general? Like,
Yeah, Maya, you
we
broke
make
up.
like
Maya, can you
we have
maybe
an
repeat
yeah.
Can you repeat because
the last?
you
Yeah,
broke
Yeah,
up
this.
there?
yeah, sorry. Yeah, just a second. Yeah. So should I start with this slide?
Yes.
Yeah. So I was trying to make a point of how does one approach this problem in general, that given an arbitrary specification, do we have an algorithm to make an automata, and surprisingly we have an automata like construct like given a specification or given a, so even like specification could be given as a set of positive and negative examples. Like in the previous slide you can look at the language L is a set of positive examples, and let's say L complement will be set of negative examples. So given positive and negative examples, can you learn an automata that accepts positive examples and rejects negative examples? So apparently uh, there are apparently a bunch of algorithms now, but one of the first attempts at this problem was made by Professor Rana Angluin, and she proposed this paper in which she proposed the L-star algorithm in 1987. So we'll just look at the overview of it, the core idea, and uh, just a little bit
One
dive into
question I
it.
had
So
there, maybe
yeah,
this will, in the previous
yeah,
slides, okay, maybe this will,
yeah,
as you
yeah,
give detail, it gets answered, in
yeah,
which case you can defer it.
yeah, yeah,
How do these methods, see, there is this question, okay, you said membership and
yeah,
then example,
yeah,
non-example, it's fine.
yeah, yeah,
What if my specification itself is wrong in the sense I give a non-regular language? Does it, I mean, you expect it to say, obviously you don't expect it to say, oh,
right,
I can't synthesize it. Okay. That
right,
recognition that
yeah,
this,
yeah, yeah, yeah,
what
yeah,
you're giving through these examples, non-examples,
yeah,
I guess the specification is not given separately.
yeah,
My question is a kind of two-part. The specification is
yeah,
not
yeah,
given as a regular language or anything. I mean, obviously, the specification is to be learned.
yeah,
Therefore, the
yeah,
I guess I'm answering my own question. So the
yeah,
expectation is through this
right,
query,
right, right,
it
yeah,
has to
yeah.
produce a regular language or an automata. That's all. Yeah. Yeah, okay. Yeah.
Yeah, yeah, yeah.
Is that right?
Yeah,
Yeah.
because so L-star deals with yeah, yeah. I should have yeah. So L-star deals with a DFA, like the original paper deals with a DFA. So DFA, any language that can be represented as a deterministic finite state automata,
Is all
is
that it can do.
a regular language. Yeah,
Yeah.
yeah.
Okay.
So
I got it.
yeah, so there are yeah, 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 yeah.
Yeah, you're
So
about
so
to
just
say
a
there
quick
are
yeah.
you're about to say something. Yeah, can
I
you
think so. I'm not sure, but I think now there are algorithms to learn other models as well. Yeah, yeah, there are. So even so recently last semester, Shrijit from IIT Goa, I think he gave a talk on learning one counter automata. So people are
I
also
see, I see. Okay, there are
building. Yeah,
such.
yeah, yeah, yeah,
Okay,
yeah, yeah,
okay.
yeah,
You
yeah.
got it. Yeah, go ahead, please.
Yeah, sure. So I'll start. So this is this picture itself not a quick overview, but it's I think this is a general setting in any learning algorithm. So one sec, yeah, yeah. So this is a general setting that is used in any learning algorithm, which is used by other algorithms as well. That is, there is a teacher and a learner model where a learner aims to learn the DFA that is unknown to the learner but known to the teacher, and learner can ask two types of questions to the teacher, which we discussed in the previous conversation. That so learner can ask a membership query to the teacher. So teacher knows the language, uh, teacher knows the unknown language, and teacher knows what are the positive and negative examples, or what, or like let's say all this uh, uh, equivalent notions, that teacher knows the language, or teacher knows positive and negative examples, or teacher knows the DFA for the language that a learner is trying to learn is, and then the objective of the learner is to learn the DFA by herself, by with the two types of tools that she has. Is she can ask membership, so given she knows what alphabets or what kind of words are, uh, I mean, so she will ask, uh, given a word, is the word accepted in the language to the teacher, and that is the membership query, and the teacher will respond with yes or no, where this is in the paper. In this paper we slightly tweak it with yes, no, and unsure. We'll look at the reasons for it, but this is the general model. And after a certain point, the learner hypothesizes an automata, which learner thinks, or like which learner either thinks that it is the correct automata, or learner tries to learn from, so the learner makes an equivalence query, that is the automata that the learner hypothesizes, is it the required automata or is it the desired automata? So the teacher replies with, either teacher has two types of answers. It replies with an yes, or it says it does not, it's not equal to the automata that we're trying to learn, and it replies with a counter example, which is in the language, but in the desired language, but learner does not, learner's automata does not have, or it could be either way, like either. So there are multiple approaches that, if like it could be like it that learner might under approximate or over approximate depending on the counter example input. But this is a general setting of the L-star algorithm. Yeah, this is what the these are the words of the previous diagram or flowchart that I was explaining. And I wanted to show the formal proof that Dana Angel has given. So I'll not go into the detail of it. So
Yeah, you
I
said the learner could under approximate or over
yeah
approximate. Of course,
yeah
there's the third thing. It may be neither an under approximation or an over approximation in the sense
it's
at
just
any
like
point
yeah
what the learner guesses,
yeah
the guessed maybe neither also, right?
right true. I yeah, I agree. Yeah, actually,
Okay.
yeah. Yeah. So I will not go into the detail of it, but I'll tell the crux of the. So this was the general setting in any learning algorithm environment. But so what L-star does is, what the uh, benefit or what the novelty of L-star was then was L-star tells us uh, what kinds of, or what sequences of membership queries should the learner make, and when to ask the equivalence query. So because equivalence queries are supposed to be expensive, and also asking arbitrary membership queries will take us a really long time. So L-star gives a polynomial time. Uh, you, so in L-star you ask membership queries in a sophisticated way, and then you realize you cannot ask more than that unless you hypothesize an automata, and then when you get a counter example, you again uh, assess what kind of membership queries you want to ask. So even the correctness proof and the detailed algorithm might be out of the scope of this presentation. Like I tried, but it would take like I also have to. So yeah. Uh, so yeah, I was just trying to say that L-star algorithm is it just tells us what kind. So what type of membership queries one should ask smartly to learn the automata in a polynomial number of time. Like
So
like
what is
polynomial, yeah.
Yeah. No. I think you're explaining that itself. Yeah. Go ahead.
Like polynomial number of times in
No,
the
no, no. I
number
mean,
of
before that,
states
I
of
got
the desired object.
distracted. I mean, what
Yeah.
is
Yeah.
SET? Okay, S
So
is
I have not thoroughly gone through this proof, sir.
oh,
Okay, so the crux, I will still try to attempt.
hmm.
But so L star algorithm is
Maybe
supposed
as you
so
go
the
explain,
yeah
it'll be clear. Go ahead. Go ahead with your
yeah
train of
yeah
thought. Yeah.
so yeah so I just wanted to show this slide because it's
Mm.
an important algorithm in the learning theory. Like yeah so in the so L star algorithm's crux is uh, to make observation table where SCT is components of the observation table. I apologize, I don't have slides for it, or I will try to annotate if I can. I'm not sure how to annotate. I, I'll try. 1 second. Just a second. Like I thought if we go into the depth of SEP, it might just take time and we will
Fine,
not be
fine.
able to.
Yeah.
Yeah. So I was just the point I was trying to make here was that L star is it tells us a sophisticated way to make these membership queries and equivalence queries, like when to make an equivalence query. So keeping this picture in mind of what it's a teacher learner model. We'll look at a running example that we look at the running example that the paper deals with, which also is the example from the other paper that this algorithm paper. Uh, so it's borrowed from there. So consider an 8x8 grid world where it could we can imagine it as a game where it could be an open world game, but let's for simplicity let's say it's an 8x8 grid game where you are an agent. You just like appear in one of the white boxes or you spawn in one of the white boxes and white tiles, and then let's say these red tiles are lava, and your target is to, and there are like different color tiles where the blue tiles represent water, red tiles represent lava, yellow tiles are the target tiles that you want to reach, and there is one uh, specification or one requirement in the game is that you can't reach the yellow or charging tile if you are wet, because yeah, to make sense of it, like if you're wet and you reach the charging tile you might get current. So there is a there is a brown or orange tile where you can dry yourself as an agent and reach the yellow tile eventually, like once you are dry. So this is a grid world, and but also there is a catch here is that the paper smartly tries to model this as a Markov decision process by assigning 1 by 32 probable. So agent can attempt to make one move at a time, up, down, left, right, and there is also 1/3 chance, because it's windy, supposed to be downward windy, that there's a 1 by 32 chance that agent might slip down because of the wind. So this is modeled for the simplicity of this algorithm that we'll look at later. But yeah, this is the given setting with the example. Should I proceed? Yeah. So how does an example or example path or a sequence in this problem would look like is that will be a sequence of colors of tiles. Like you can either start with yellow, yellow, blue, yellow. So we can actually uh, so for the so the white tiled uh, paths or white tiled walks are not useful for our for the information that we want to learn or the automata that we want to learn. So here we only considered the yellow tile or the color tiles that we encounter. Just a second.
No, I have a question here. Why is this? Okay, I can see.
Yeah.
No, I don't
Yeah.
obviously see why this problem, this grid world problem,
Yeah.
you want to
Yeah.
reach. Okay, so how is this
Yeah.
cast can be
How
cast
is
looked at as a DFA learning problem?
So
Going to
yeah, I
explain
have
that?
added.
Huh?
I have added a slide in the next two
Okay,
slides.
very good. Fine.
Yeah.
Okay.
So sure. Yeah. I was actually doing the mock presentation and I did not have the slide.
Mm.
But one of my friends suggested that having the DFA would actually help, like clarify. Yeah. So it's in the next two slides. Sure.
Okay.
So you can see that how if you actually go from red, just this is just a clarification that you can merge the consecutive same color tiles into one, and that is the information that is required to learn the automata. So the objective here in this grid world is to learn a DFA that will accept the path that follows the given rules. Like, let's just formalize the rules that the agent must eventually reach yellow tiles. Agent must avoid lava at any cost because lava is harmful to humans. So and then if agent gets wet, it must go to an orange tile to dry off before reaching the yellow tile. So these are the specifications, or these are the given rules. Like, let's not use the word. Yeah, these are the given rules for this grid world game or grid world example that we want to make sure. And just wanted to show the target automata first before learning it. Is like, it might look like this. Is like, you start with a white tile,
Mm.
and if you reach a yellow tile, you will just you the and you don't go anywhere else, then
Mm.
you are accepted. If you encounter a red tile by any chance, you
Mm.
will never go to an accepting state, or the path will never be an accepting path.
Mm.
And here, this could be like one rule can be modeled like this, and if we are to model all three rules, or like and incorporate all three rules, it could be that you should reach yellow tile eventually, and do not go anywhere else. It would be this right side of the automata, and if you encounter a blue tile, then you must and if you encounter a blue tile and a yellow tile, it will never be an accepting path, because you might get shocked, like in the real world or natural language or natural understanding of the world. We can think of it like that. But that's why there's a blue and a yellow will never reach the accepting state. So only way to reach from a blue tile, you have to go to the dry tile, and then you go to the yellow tile. Yeah. So, and then if you reach here, then a red tile will go here, and a blue tile will make sure that you reach the brown tile before you reach the yellow tile.
Mm.
Yeah, this is the target automata that we are trying to learn. Uh, so now recall, so 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 the so recall that L star only tells us that what kind of membership queries we want to ask, but who do we ask the membership query, or who do we in real world, who do we look up to as a teacher, or who do we sign up as a teacher for, or what the oracle or a teacher, uh, who do we go for is so here we attempt to approximate a teacher, or we attempt to find a teacher in the form of LLMs. So in the membership query, at least we go to this one. That our, like, for simplicity, we can say that our teacher here is an LLM. Where so LLM sort of LLMs offer a natural approximation for membership queries. The author has claimed this. And then so what a learner will do is ask the membership query. So you will be feeding. Do I have it? So yeah, I do not have it, but yeah, it's in the later slide that. So what you do is you feed LLM a bunch of positive and negative examples. Along with that, you also feed LLM the natural language prompt, or the given rules that we want our automata to form, and then as a learner you ask the membership query that is the is the given path here in this example, that is it an accepting path, or is it a valid, sorry, excuse me, is it a valid path? And then LLMs tend to will be answering yes or no, or we'll see that this paper has also used the option of unsure. LLM could answer unsure because so yeah, we'll see in the next slide how it would look like. So to formalize the DFA interaction.
So just a
Yeah,
short question here.
sure.
So just to understand, I mean, see, when
Yeah.
you were talking about the L-star algorithm, when you say that, okay, we want to learn a DFA from something like a specification, whatever your teacher, whoever implements the implementation of the teacher is essentially what gives you the specification, right? And now here, if I understand your examples correctly, the specification is in some combination of natural language and some examples of these labeled states. So
Yeah.
we want to ultimately understand or to come up with an DFA that adheres to the natural language specification while also producing examples that or producing or accepting sequences of states that look like the ones given in the examples. Is that at a high level the goal that we are aiming for it?
Yeah. I think yeah. So can you repeat the second part? So you said that it must adhere to the
Yeah. So
natural language prompts and yeah.
correct. So I mean, what is the DFA that we're trying to learn? So is it a DFA that should be given a natural language and some examples?
Yeah.
The question is, give me a DFA that adheres to the natural language spec, and if I actually look at the language, then the words in the language look like these examples.
Yes. Yeah. So yeah, this I think the title of the paper is that learning automata from natural languages and the guided exam. If I'm getting it right. So I think yeah. So it has to adhere to both of the
I
specification.
see.
Either.
So at this point, that is
Yeah.
the kind of working model. So here, when you're saying, for
Yeah.
example, that here's LLM and querying with some kind of a learner and so on. That the DFA that the learner and the LLM are trying to come up with is something that should adhere to these kinds of things. That's
Yes.
what, right? Yeah. Okay. Sure.
Yeah. So we'll just formalize how the interaction with the LLM.
Yeah.
Sure.
The LLM here as a
Yeah.
following up the things.
Sure.
Earlier, the teacher was a knowledgeable teacher. So here, LLM is a perfect teacher. So
Yeah. So
that,
yeah.
mm,
True. And we also realize that this teacher is not just sufficient. So we adhere to the expert demonstration under this algorithm. We'll look at in the later. Yeah. So yeah. So this is a general LLM interaction with so like a language model takes sequence of tokens, or it could be like the sentences or the queries that you ask to an LLM. It's called prompt, and then LLM responds with gives the response. We call it response, and Y is the response, and then Y can be extended as a membership oracle or the answer for the membership query. So the grammar here they have used is uh, for so in the answer it can answer yes, no, or unsure. This they do because so LLMs tend to hallucinate uh, in and even in general you sometimes ask for some questions and they like especially math questions and they give wrong answers confidently. So to avoid that part, we give LLM the liberty to say that it's unsure.
yeah, but
And
here in
like
the formalization, Maya, you
yeah,
say
yeah,
here a prompt is presumably what is going from the learner into the
yes,
LLM, correct?
yeah, yeah,
Outputs are what the LLM is producing. But why
yes,
is the Y also belongs to tau star? Oh, so you're combining the prompt
yeah.
and response as tau star?
No, so I think the tau star is it. If I'm not wrong, then it represents the natural language or the so it the prompt the response answer will be of this form. That final answer is yes or no or unsure. Like
I see. So basically, both the prompt and the response belong to the same language defined by Taustar with their formalization.
Yeah, some subset of it could be the end thing, like yes, no, and unsure. Can also produce certain things which can then be incorporated into the queries, etc. So you want to allow for that thing, I guess. Okay.
So I have a question then with respect to this formalization. I mean, if this is better answered later on, just feel free to defer. But see, given this formalization, it seems that the grammar has been set in such a way that the LLM can potentially respond with everything except for the answer, right? I mean, so for example, it can just go like, I mean, it can have a lot of things before the answer, right? So it can say that, okay, just go, final answer. Oh, okay, okay. No, but then, okay, so this grammar, if this grammar is in, so is this grammar defining tau star or?
No, I think
that's not.
grammar is part of the subset of tau.
Right. Okay. So the grammar only applies to when the LLM is generating the output, and then the input can be something more general in terms of tau star, which is whatever the whole natural language.
Totally.
Okay. Got it.
Like we'll look at an example from the paper as well.
Yeah, sure.
So so just another thing that so the response is generated by the 1 second. So we formalize what are we going to ask the LLM is like what does a prompt look like? Here it'll be more clear like what kind of prompts we give to the LLM or the paper gives to the LLM is it gives the instruction for answering the question like how does it want to answer, and it requests to show work, and it also gives known labeled examples because we have the liberty of knowing what the positive and negative examples are like, and the membership query realized that the text is this given path positive example. We'll also look at the example, like the concrete example. The sample interaction is like a robot is operating in the grid world. Like you specify your problem, like how many tiles, like what color tiles are there, like and what each color correspond to, and the robot is to visit tiles according to some rules, and then the rules here are given below that we have looked in the previous slides, that the 3 rules that we have looked at, and then the positive examples, and it also says that a positive example must conform to all these rules. And then it also gives the examples. It's a continuation of the prompt that will be given, the learner will be giving to the LLM is for example, like these are the parts. So this is here it's telling how do we how we are merging the consecutive same color tiles into one as it's easier to read, and additionally and it's easier to it's helpful, it's actually helpful to make automata like that. No, and then additionally by so so these are the positive and negative. So we are also telling LLM that we will be dealing with the demonstration of the task, which we'll look at in the later, like in the next few slides, that this line we'll look at later. And then these are the positive and these are the negative examples, and then it clearly tells the instruction how to answer. It's like, please briefly answer the following question using step by step. So do not answer. It is amusing to see the do not answer any more question here. But when you arrive at the conclusion, please answer. Like this is how we are telling. In this interaction, they have only given final liberty to LLM to only say yes or no. In the experiments, they give both yes, no, and yes, no, and unsure to compare if it is better, which one is better. And then so the response of AI could look like to determine if this is a positive example. We need to, so I think I have cropped the AI's response here, but this is how the prompt would look like, and then response will be either of this is a positive example, yes or no. So if this is clear, I move to the next slide. Am I audible?
Yeah, that's
Yeah,
clear,
yeah,
more or less. Yeah,
sure. So
at least for me.
okay. So yeah, 1 second. Yeah. Yeah. So finality guarantee that. So this is the picture that will explain what we looked at in the previous slide. Is like we feed natural language prompts to the large language model, and we feed positive and negative examples to learner and the large language model LLMs, and and we maintain a cache layer to uh, keep the memory of what membership query has the large language model answer. And we also, this is also to so that if we have the unsure, if we have the responses unsure, it might not be useful for a learner, but we'll still store it so that we'll probably just skip and move on to the next membership query. Yeah, so this is how the interaction with the DFA, LLM interaction with the DFA, or like the one part of the algorithm would look like. So we look at where it could fail. So suppose you forget a condition and the DFA interaction,
No, can
then
you go back to the previous thing? I want to
yeah,
understand that
sure,
flow
yeah,
completely.
sure.
Now, the L star, the way you introduced earlier,
Yeah.
was itself was a teacher or learner in that thing?
So it's so this is so I'll explain why. I think your question is why the learner is bracketed as L star or SAT, right?
Yeah.
If I will, yeah. So uh, so we have learned that learning algorithms have this learner and a teacher model,
Mhm.
but what kind of membership queries one would ask, that can vary from like depending on what algorithm are you using, if it is L-star or there is some other algorithm SAT or like using SAT. So I think this is not the whole of L-star or SAT, it's just what
Okay.
kind of membership query. Yeah.
Mm.
Like
Okay.
like the learner strategy, this is what the learner strategy is different. Yeah,
So mostly
I
here,
think that.
the learner is also a checker. L star is being more like a checker, okay? And
uh,
then, I mean, it can check whether it is.
I'm not
No,
sure.
no, 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 no.
So
See, because
I,
you're saying,
then, yeah,
because
yeah,
you're saying, no, S no
yeah,
sure is actually, no, it's the other way around.
yeah,
Okay.
yeah,
It's coming
yeah,
out
yeah,
from from the language
yeah,
model. Yeah.
yeah, it's just getting the
So
information.
just like you said, L
Yeah,
star is kind of that component that generates the queries
yeah,
is what is
yeah,
being used
yeah,
here.
yeah.
Okay.
And the strategy of the query, it depends upon what, if you're using L-star or
Mm,
some other learning algorithm.
mm,
So I have
Yeah,
a couple of questions here.
yeah,
Firstly, ultimately, even though we have like the user has given us some concrete ground truth, positive and negative examples, is it the case that we are still going to ask the model if a known example is a positive example or not? Then the
no,
model can potentially give a wrong answer and confuse everything, right?
yes, I think that's why they have made the layer of cache to store.
I see.
If yeah, like
mm.
to
So
avoid
the
that
cache
from
is
happening.
so the cache is
Like if
initialized with the given examples from the user.
yes, yeah, we
History,
are
I
like
think it
in
stores some history.
the add is like we have fed cache also the layer of like positive and negative examples, like the information.
I see.
So
Yeah,
cache
yeah,
can,
Okay.
if a language model, following up with
yeah,
this thing, if it contradicts its previous answer,
mm.
Yeah, that is another question that I had. Yeah.
I mean, I
What
guess
what happens then?
what will happen then?
Could you repeat, sir?
No, let's suppose since the language model is not the
Yeah,
perfect uh,
yeah, yeah, yeah,
teacher, it
yeah,
can say, well, you know,
yeah. It can answer no even
yeah,
instead
it
of
can
answer. It
contradict
can,
something that it has answered one
yeah,
way
yeah, yeah,
earlier.
yeah,
Huh?
yeah,
So
yeah,
then, will the learner at least be able to have enough
yeah.
capacity to say, hey, look, you answered it something like this. Now you're doing it like this. Okay, that is a checking. I mean, that's what I said. The learner may not know the ultimate answer, but at least that's why I've asked the question if it has some capability that, oh, your answer is inconsistent. This is not what the thing is, and so on and so forth. Now, so that because you had SAT has that capability, and Elsa.
I'm not sure, sir. Sorry. Yeah, I think in this setting it will not have. I don't think learner will have a capacity to verify if.
No, maybe not fully, but at least the one where inconsistency in the previous answers, will that the learner be able to catch? Okay, otherwise, what is the use of cache? What is the use of cache?
I think, yeah, that will be helped with cache, but yeah, if we can consider cache and the learner as a whole as a learner, then it has some capacity to verify. Yeah.
Okay, no, so now that is a bit confusing because see, at least within the context of LSTAR, once the learner has made a membership query, it does not expect that in the future the result of the membership query would become wrong, right? So, for example, suppose if there's this particular some orange, yellow, blue, right? What happens in the situation like this? The learner makes this query. Is this a positive example? The language model says yes, right? And then the learner makes this query again, and then the language model says no. Now, at the cache level, we can clearly see that this contradicts with the previous history. But there is no way we can tell the learner that, right? At least if we follow the interface on the LSTAR, right? Because LSTAR, we can't tell LSTAR that, oh, no, I changed my mind about this particular word now, right?
Yeah. I don't think the paper has dealt with this case.
I see.
Yeah.
I see.
Yeah, I'm not sure how it is impacted. Yeah.
I see.
Yeah.
That's kind of interesting because I mean, from what I've seen in some other LLM based some sort of neurosymbolic works where they combine LLM with other things, this idea of whether the LLM is consistent with itself is given some weightage in the sense that if the LLM is considered whatever the answer the LLM gives, it's considered more trustworthy if it is consistent with whatever it has said before or after in any sense. They're not doing any sort of this kind of a consistency analysis.
I'm not sure, but they are assuming that it won't be foolproof, and they're like in the next slide we'll see where this might be.
I see. Okay, sure.
Like, so and then we lean on to the expert demonstration and this. Yeah.
Okay. Just one final question. You see, I mean, so far, of course, LSTAR, given the interface that you showed for LSTAR, the learner kind of can make two kinds of queries. So far, you've only been dealing with membership queries. I guess later on you'll talk about what if the learner wants to make an equivalence query? What happens, right?
Yeah, totally.
Okay, sure.
Yeah, sure. So where we'll see where the interaction with the LLM, where it could fail, and suppose you forget a condition or suppose you forget a rule that DFA must adhere to, and then LLM, then it is unfair almost to expect LLM to guess the correct DFA, and then additionally, if LLM hallucinate or might misbehave, as they have mentioned, they have only mentioned that so because you don't trust LLM enough, and it also is just membership query. Like they next technique is like used to rectify the potential issues. I'm not sure if the specific question Diganta and Sir you asked will be addressed, but we'll see if I'll also try to filter. Yeah.
So just one small question here. Just sorry for interrupting, but I mean, so far at least the LLM is not doing any kind of guessing of the DFA, right? I mean, in the sense, all the guessing is being done by an LSTAR algorithm. All that the LLM is doing is telling whether a given word follows the natural language spec or not, right?
Yes. Yeah. We haven't done with the equivalence query. Like, yes.
Okay.
So we'll just look at this another technique called expert demonstration. It's a detour, but also for him, like just we look at another component that we are using called learning from expert demonstration. So what an expert demonstration is. It's a path generated in an MDP by a policy optimized to satisfy
So
unknown.
sorry,
So
Maya. I mean, I
yeah,
have
yeah,
to
sure. Yeah, yeah,
interrupt here
yeah, yeah,
just to ensure that the question
yeah,
that Diganta asked earlier, okay,
yeah,
kind of, got clarified, and I want to make sure that
yeah,
you agree with that, and
yeah,
then we are the
yeah,
same. Now,
yeah.
if I
The
understand,
thing is, yeah,
so here the
yeah,
idea is to use LLM to improve L star, correct?
yeah,
Is
yeah,
that the goal? Which means,
yeah, yeah, yeah. Hmm.
so that's why LLM is being used, and I thought that's how I understood Diganta's question, that LLM itself is not, guessing the,
Hmm.
so. Uh,
Yeah,
so L-Star is actually using LLM as a helper, and
yes,
so
yes,
to ask
yeah,
it
yeah,
to
yeah,
help it improve its own algorithm
yeah,
in trying to synthesize
yeah,
BFA.
yeah,
Okay.
yeah, yeah, yeah. True. Like we're also looking at uh, so there is a technique called backend elimination.
Okay.
So
Okay.
I'm
No,
not,
that context is
yeah,
fine. So which means LLM
sure.
introduction has a certain
Yeah,
specific
yeah, yeah.
purpose.
We're using it as a tool to
Okay.
replace, use it as a membership
Yeah,
query only.
because in the way that you made that picture, it looked
Yeah,
because you call the
yeah,
LLMs as
yeah, yeah. So
teacher,
yeah,
that's why it becomes a
yeah,
bit
yeah,
confusing. Yeah.
yeah. So I, if I go back, I made sure that it's only dealing with the membership query here.
Mm.
Sorry if it wasn't very clear. Yeah, it does not deal with the equivalence query.
Okay, okay, fine.
Yeah, 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 yeah. Sure. Yeah. Let's look at this technique called learning from expert demonstration. We'll discuss the this sentence that it's a path generated in an MDP, generated by a policy optimized to satisfy unknown specification task. There's a lot in here. In the next 5 6 slides, we'll discuss. So we'll look at what an MDP is. It's a Markov decision process. It's a four tuple. It has states, actions, transition probability. It can be seen as a computational model, slightly different from a DFA. We are here now. We are dealing with a Markov decision process. So in a Markov decision process, how a path would look like is S naught A naught. So these small S and A, these are states and actions. So if we recall that an agent can make a move or take an action. So this is what the A naught A1 represents, and S naught S1 represent to the states of the automata that we're trying to learn. And then there's this function called feature map. It extracts event, as in it takes the path and make it as the like uh, like how we combine the non-consecutive color tiles into one and drop the white tiles. This is what this function does. So given yeah, we'll just formalize, given a DFA, that a path is accepted by D if f of uh, uh, f of eta, if I'm using it right, f of eta is accepted in the language of the DFA. Like yeah, so the f function basically makes the path readable by an automata. So yeah, f maps the grid world to the sequence of uh, just a second, sir. I am getting a yeah. Sorry, I one of my remotes. Yeah, so we can like just to recall that our running example is also modeled as an MDP, like a Markov decision process. We saw that the wind is flowing uh, with the downward direction. I'm sorry if it is an there's an interruption. Yeah, yeah. So uh, yeah, so the we see that it our original the running example is modeled as MDP using the downward wind of probability 1/3 with every action. So now we are coming back to what an expert demonstration is. Before that, we look at what a policy is. A policy is a mapping from a path to a distribution over actions. This is like this is a stochastic policy, a definition of a if I'm right, yeah, this is a definition of a stochastic policy that it maps a path to a distribution over actions. Like it just assigns with what probability a path is like. Yeah, they have not defined exactly, but it just assigns some probability to a path. So finally, what an expert demonstration is that it's a path generated by the policy or is the policy that we have in hand, and then it tries to generate a path accepted by the automata. The it's yeah, and so what an expert policy tries to do here is to produce a path that a true specification would accept. There are a lot of things. I mean, like it's not very clear from here, but we'll look at it in the next few slides. These are a lot of definitions. I think I found it a little difficult to understand. But we'll look at what first we'll look at what the difference between an expert. So we see that an expert demonstration and a labeled example, both of them are paths only, like a sequence, like like paths that are accepted by an automata or not. But like they have the same, they represent similar sequences, but there are significant differences in what a labeled example is and what an expert demonstration is. So unlike labeled examples, an expert demonstration it might not necessarily satisfy the true specification. Uh, so we here the labeled example is the either label example here we are dealing with is so if you uh, so here we'll deal with would not just to go back to the question that you have asked was the because we will be using labeled example in the dis algorithm, like the newly generated ones, but the labeled examples generated from the LLM interaction would not be used here. So uh, I think I think that was what I realized now when you have asked me that question. It will I think it will be clear in the next slide.
So I just have one question here. When
Yes.
talking about the difference between labeled examples and expert demonstration, is it
Yeah.
correct to say there was an MDP and there was a feature map, right?
Yeah.
Is it correct to say that an expert demonstration is going to be a path in the MDP, whereas labeled example is just a sequence of feature map outputs? In the
Yeah.
sense, I don't, I mean, is it the case that, so for example, there's two things, right? There's two kinds of ways we can look at a path here.
Yeah.
In the grid world example, we can look at the actual locations, or we can say just, oh, yellow happens, then blue happens, then yellow happens, and then blue happens, and so on, right?
Yeah.
So when we're saying labeled examples and expert demonstrations are both paths, are we saying that both of them are the former, both of them are the latter, one is the former or one is the latter? Which of these is it the case?
Yeah. So yeah, I'll try to answer. So I think so. First of all, we know the correct output if it is a labeled example. If a path is a labeled example, then we know the accurate output. Like if the path is accepted or not. Like that is the feature of labeled example. Like feature not the right word, but like don't want to confuse. But that is the characteristic of a labeled example that we know exactly precisely what if it is accepted or not in the given DFA, like by the given DFA. But on the other hand, expert demonstration is a path generated by some policy. We look at what just we'll just touch what kind of policy. So here, an expert demonstration is a path generated uh, by policy to that tries to learn something from the like. Okay, just a second. Let me read. So expert demonstration. Uh, can I address it in the next two slide? The question.
Yeah. Feel free. I mean, if it is addressed later on, then just
Yeah. I think that would be more clear. Yeah. So I'll just discuss how. Yeah, I think this slide could have been later. But yeah, so expert demonstration.
Yep.
Uh, I'm
Somehow,
just saying that expert. Yeah.
no, go. Okay, fine. Go
Yeah.
ahead.
So the expert demonstration, I'm just saying that it's we are not sure if it is a we can't just simply say that if an expert demonstration is positive, like if we can't simply label it as a positive or negative example. Will it is so we there in the next slides it will be clear why. Uh, so so if you take it for mm, one second, I'll just uh, yeah. Yeah, I was just thinking of the way Diganta framed, like tried to think of expert demonstration as just a like just a output of the feature map. I think a labeled example is also an output of a feature map, uh, but expert demonstration is a directed path, or like a or like just some path generated by a policy. We look at in the next slide why it matters, like why the policy matters, or like so expert demonstration is it's these are the demonstrations generated for a purpose, like we are like this the algorithm that we'll be dealing with it deals with the expert demonstration. We'll see how, or so I'll just try to see like if I'm able to answer it in the next slide. Yeah. So we are just if you
Sure.
take it in the value that expert demonstration are not, we can't just simply use the expert demonstration for our the membership query or equivalence query, but also we look at what the dis algorithm does here. So this algorithm we are using as a so we looked at how LLM was used as a membership query oracle. We are using this algorithm here as an equivalence query oracle, like approximate or like it is an equivalence query algo equivalence query oracle. So we look at what formally what this algorithm is. It's a inverse enforcement based algorithm which alternates between hypothesizing labeled examples and sampling candidate specification to explain the demo. So and it makes the demonstration. One second. I'll just have some more. So this is from what I understand is this is a we are using this as an equivalence query oracle, and where the learner hypothesizes uh, a DFA and it gives it to this, and then this works out so this is black box here, but then this what this does is this generates a policy uh, to to generate the expert demonstration, and then it compares expert demonstration using some parameter called energy. We'll see in the next slide how and it deals how it compares. And just uh, just a note here was that the policy generated by the disk is a maximum. It's based on this maximum causal policy, causal entropy, maximum causal entropy planning. Like so, just to look at the chart of like how flow chart is like just more details of the disk algorithm is that it treats demonstration learning problem as iterative loop. We'll see. So it starts with whatever examples and specification we have, or like in the middle of the disk, you can see it like it has some examples and some specification, and then at each step it infers new labeled examples, and then it then it then it one sec. Hmm. Yeah, so at each step it infers new labeled examples, and then it gives back to the learner, and it also like and you also check if it is the checking of the equivalence query is dealt with the energy parameter, that they have defined in the later half. So there are two components of the disk itself, that it has a sampler that, given a given labeled examples, it returns candidate DFA consistent with those examples. So this so what we are saying here is, I think the explanation how an L star works would have been helpful here. That uh, so L star makes observation tables mainly with the membership queries. Uh, so so from that observation tables, uh, we know how to make how to make a DFA similar to it or consistent with the observation table. That's what the sampler does. So for this part, this can be done manually as well, like manually or SAT solver or using LSAT. But what the planner does is, it takes the DFA using the previous labeled examples, and or could be the observation table, or yeah, taking this labeled example, it takes the DFA generated by it, and then it computes entropy regularized policy. That is a maximum causal entropy policy. We'll see in the next slide that the what kind of policy it generates is like, so the planner so the planner uses maximum causal entropy inverse enforcement learning, which means that it produces a policy that maximizes the entropy while matching the candidate accepting condition. Uh, what what you mean by this is, given a DFA, it 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 traces all its paths and assigns a certain probability to each path. Like, to every path, it assigns probability, some probability, and by maximum causes, like it explores all the paths. So here, if you look at it, that it's we saw that this algorithm is a iterative loop. So it will start with minimum examples and minimum specification, or like whatever that is give in hand. Then it builds upon it to learn, add more state and have more examples. So so it, in the initial half, if you look at it, this part was not covered in the paper, but I had to, like, I tried reading upon it. And so just an example of what this policy would look like is, like, we can say that, okay, first in the first DFA, that it only the uh, in the sampler only gives us this DFA which adheres to the rules that reach yellow time. This is the only specification that we have. And the maximum entropy policy then will assign, so if it has no other rule that you should not avoid lava, if that rule is not there, then the maximum causal entropy policy will assign paths to will assign non-negative probability to paths even through lava. And like, yeah, and it also assign paths probability to paths that does not go through lava. And it will be a distinct, like, varied the probability. So the reason I'm emphasizing here is that it's not a deterministic policy, that given a DFA, it does not assign 100% probability to one single path. It spreads over all the paths, like, such that we cover all the paths. Uh, so here the assumption is, like, in the middle of the dish algorithm, we might not have the correct this is the assumption that we will not have a correct automata. So we want to explore all the different paths that might be positive or negative, and we'll see how, like, if it is if the word uh, we'll compare the probability using the energy function. I think it will be in the next slide. So here I'm saying the probability generated by this doesn't just pick one optimal path, it spreads over the probability over various paths, like all the paths, ensuring like taking account of all uncertainties. So just the flow overall of this algorithm is it proposes a DFA first, and then it computes the maximum entropy policy. Then it uses the policy to interpret the demonstration. Like the demonstration generated, it uses that policy to interpret the demonstration and then make hypothesize new labeled examples. We'll look at an example how it hypothesized, and then add these examples in the buffer and update the examples in the next round. And it stops when more, so that this is the termination condition is that they do it using the energy parameter. We'll see how they define it. Is like so you define the energy uh, of the automata and the path with that this I'll just read it. It's like so energy is defined as the sum of negative log probability of the path given that policy and the size of the automata. So you can read it as a this negative log probability as a demonstration surprise, or how surprising is that demonstration given
I
the
mean, I
DFA
have here a
policy.
question. I
Yeah,
think,
yeah,
how exactly DISS is used in the larger scheme of things and what is your
yeah, yeah,
is
yeah,
kind of not very clear. So until
yeah,
now, you were using LLM as an assistance
yeah,
to
yeah,
L-star to get to
yeah,
something. Now you're switched over to this reinforcement learning
yeah,
framework.
yeah, yeah,
You're going to link the two to see where is
yes, yeah,
LLM.
yeah,
This LLM doesn't seem like playing a role
yeah,
at
yeah, yeah.
here. Huh?
Yeah, yeah, it is there.
Okay.
It's in the
We'll
like
come to that.
yeah.
Okay.
So
You're
how
just
we are
describing
yeah, yeah,
the
yeah. So
DISS part.
yeah, yeah, which is important to
Okay.
model it as a equivalence oracle, like equivalence theory oracle.
Um,
Yeah. So they define energy of a given path respect to the DFA, respect to the current DFA, using the demonstration, like this notion of demonstration surprise, uh, like how surprising is that path given to that policy and the size. This they're trying to do because L-star also tries to so L-star. Just a side notation that L-star always gives a minimal automata for that specification. So here also they are taking account of the size. So it will only it terminates when the energy does not decrease beyond a certain limit. So it just to note that it also tries to aim for a minimal automata. And so the goal of so we'll look at the example of how the disk works, and then we'll see how the LLM is being used here with this is, let's say the current DFA in the disk loop, the algorithm loop that it only enforces that avoid red tile or the avoid lava and eventually reach yellow tile. So under this DFA, an expert going from the brown tile after when it goes to the blue tile and it goes to the brown tile. This is a surprising path because for this DFA, uh, it's much. It should be. It should. It should be. Uh, uh, it should be obvious that it should directly go to the yellow path, but it is surprising that it is covering the blue and then brown and then yellow path. So then this observe that this demo, it's like then why it does not take the shorter route of just blue and then yellow is then this interprets this as a negative example. Like if this path, so in the current list of labeled examples, we see a lot of brown, like blue, brown, and yellow. Then it interprets that the blue and yellow path will be a negative example. So this is how the disk category. So this is how from the expert demonstration, like the expert demonstration of directly going here, blue and yellow, it interprets that as a negative example, and then it injects it into the uh, negative example set, and then it proceeds to the new round. So we'll and then we'll look at how we integrate LLMs and this that author has given, that you run this with LLM based DFA interaction. So we can look at it as, so in L star, what you do is you start with a bunch of membership queries, and then you realize you cannot make more membership queries unless you ask the teacher, is the DFA. So you have like so what L star algorithm, what L star's uh, workflow is, it starts with, it makes the minimum number of membership queries, that so that it is able to produce the best hypothesized DFA, and then it will present it to the teacher, and then it will give a counter example, and then you make a bunch of other membership queries. So here also, what you do is you run this with LLM based interaction, is like you ask LLM first few membership queries, and then you ask this if we have seen that how in this you propose as a candidate, and then this will return, so this will actually just return the energy here, but then we also at each iteration, this will return some energy. It won't return yes or no, but it will return some the energy notion that we have that author has defined here. And then when you run the loop again, if the energy does not decrease, then you conclude that the DFA is the correct DFA that we have looked for. But then how the LLM is interacting here is, you for using those membership queries, to make those membership query, you're using LLM, and then in the next I think this is a visualizer that they have presented, is like you have a DFA learner, you make the membership queries to the language model, and then you reach a point where you think that this is the least amount of membership queries I can ask to learn the best automata, and then you ask this if that is the candidate automata that you give to the disk, and then this does the entropy and max causal entropy policy, and then it generates new labeled examples that we have seen in this example then, and it also generates the energy, and then again like you look at if the energy, like you terminate when the energy does not decrease. So
Okay. Now
yeah,
this
so this
picture makes it clear. Yeah. Yeah.
Yeah, and then
If the energy does not, whatever is, you converge. Okay, and then that may
yeah,
be
yeah, yeah,
a good one or or a bad one. Otherwise, it'll also help. I guess DS also helps generate these labeled examples and so on, so that
yeah, 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 yeah,
incorporate in the future
yeah,
queries.
yeah. So just to move on to the experiments of
Mm.
how uh, so this experiment, as we have seen, the example itself is also, and experiment is also borrowed from the Vasquez Chantlet paper of 2022. But the experiments here are, they do two sets of experiments.
Mm.
It will be clear. Yeah, we have, so the DFA learning experiment. So you're using L star LM in both of them, but you're changing the backend of either L star or the SAT solver, like, or the other backend elimination, candidate elimination in the backend, or either L star in the backend. So, and then they have varied some constraint that if it is a yes, like if you are allowed to use yes, no, or unsure, and if you are given all the rules, or if you have forgotten something. So we'll just look at the necessary parameters. Like, so it's like for the for for the this
Can you leave
yeah,
the
yeah, 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 I was,
a
yeah,
little
yeah,
bit? I mean, I
yeah,
want to understand what are these?
yeah, yeah. So I was just showing the next slide just to
Ah, okay. So that
explain
you
what.
can, okay.
Yeah, so yeah, so So these labels that are given here, unsure answers, and all rules, and then this query budget here, these are, so all rules as in, if, so it's all rules as in, if we are making sure, we are trying to understand if it is necessary to give LLM all the specification, or if it is allowed for us to forget, or if can you, is it, are we okay? So here they have specifically not given the third rule. Like, I will have to go back to which rule it is, but they have missed out on one rule deliberately. If it is true, then they have given all the rules. If it is false, then they have uh, like not given the last rule. And then allow unsure here is that we have looked at the response of the LLM. You only allow either, if it allow unsure is true, then you you give the LLM yes, no, or unsure, and if it is not, then it is just yes or no. So the query budget is number of LLM interactions we are allowed to make to the LLM. Yeah. So for each iteration of it. Yeah. So these are the charts we'll look at in the next slide. What are the conclusion of this experiments are. So this left side is for the that does not use L star, and the right side this uses L star. It's a little difficult to figure out just from the slides. Even I had to, like, just from the picture. But there are few things that you can guess here. Is that if the query budget per interaction, that is LLM interaction, is 0, then it is practically impossible or very difficult to in some of the, it is difficult to guess. If the, so they're saying that LLM interaction is very helpful. And we'll see in the next slide that, so say that the like if we are not allowed to use LLM interaction, then uh, it, like, it is difficult to reach the minimum ground energy or the ground truth energy that we have defined here. And even in the setting where all rules are provided, here we are trying to understand the importance of expert demonstration on this. It's like, even if the all rules are provided, we need at least 5 to 15 uh, iterations of this to understand learn a good DFA as they have defined. That's suggesting that natural language prompt is not enough. And then in the third slide, we look at how if we can see that unsure answers being true, this, while unsure answers being false, these two and these two. Here we realize that so it does not matter in the in the in the in the L star, where we in this backend candidate elimination where we do not use LLM, but here on the right side bottom half, you can look at if the all rules are if the unsure answers are false here, and the unsure answers are true here. If the unsure answers are false, we are not able to recognize the DFA, like so, and if when the unsure answer, when we allow LLM to answer unsure, we are able to recognize the DFA with given 30, like 15 to 20 iterations of this. So this is why the unsure, like allowing unsure, improves performance highly. And then one interesting observation they had is that SAT based backend candidate elimination still outperform. It outperforms when the unsure answers are not allowed. Like they're saying that allowing unsure answers improves the L star. When we, even if it have L star in the backend, it will help. So these are the observations. If you have questions, is it okay if I move to the conclusion?
Yeah, please.
So the conclusion.
Before you move, I have
a
question. So because there was no, and in the maps. How should I read these maps? I know that I was trying, when you were doing, I was trying to read this paragraph, and then I got distracted. So I mean, this
Yeah.
effort is query budget, okay, which means how much
Yeah.
red means
LLM interaction.
LLM interaction is being
Yeah.
used, blue is
Yeah.
0. So when
Yeah.
I
Yeah. Sorry. So
no,
sorry
let
to
me ask.
interrupt. Just the
So
red line is
the red
yeah.
line is
So this is the ground truth energy, I think. So this is the energy. The vertical bar is for energy. If the color is not clear, I think this is orange and blue, and they have used red dotted line for the ground energy that we want to achieve, like the correct DFA we want to learn. That energy they have given as this red dotted line.
oh, so
And
if some
just
method comes down to it, that is good. Okay, correct?
yeah.
And with with 0, it kind of stays. It kind of comes down,
Yeah,
kind of never comes down. It
yeah.
peters out and then stays there. But
Yeah.
as you increase the thing, how quickly it
Mm,
comes for predicting the correct DFA. Okay. By the correct DFA means it may not be the perfect DFA, but with
yeah,
some
yeah, yeah. Would be a good
energy and
yes,
so on.
yeah.
Okay. Now it makes sense. I mean, that at least
Mm.
the left side. What is being done in the right side?
So right side is using L star in the backend, where the LLM interactions we are using, where so when you don't allow unsure answers in the L star, you
But
when you use
unsure
L star
answers are
in
there both on the left side as well as the right
yeah.
side. What is the
So unsure
also DFA
unsure
learning
answers
instruments
is
using L star backend, whereas the
yeah.
left one is ODI
Left one is
assist
using
backend.
so L star using the candidate elimination. This word candidate elimination. It doesn't use L star. Yeah, it doesn't use LLM for the
Ah.
membership
But
query.
then if
Yeah,
it
it
doesn't
uses
use,
start solver.
oh, the left side uses
Yeah,
solver as
yeah. It uses LLMs. Yeah,
so in order to then compare, but why
like
did then
this.
if you used LLM with false, it is doing worse than SAT, no? If you in this
Uh,
left corner, it never I never see it
yeah,
touch
yeah,
the red line.
yeah,
So there is a
yeah.
case
Because
where
yeah.
this one with DISS, etc., is better, huh?
I think so. So the comparison here is about if we are. This is the comparison about the use of LLM, right? Like the reason we have two different algorithms is like the right one uses LLM for the membership query,
Uh,
left one uses SAT for the membership query. So when you use LLM,
mm,
then it is significant that when you allow an unsure answers for elements, then we get the answers like this column, like these two.
mm,
We are able to get it. We are able to reach the good DFA sooner.
mm,
It improves the performance. Like here, when the all rules are true and when unsure answers are still false, then we are able to reach, but not in the even if we forget this column that looks a little concerning is when the um, oh, oh I see. Well, so yeah, so when the unsure answers are false and the all rules are true, we are not able to gauge. I think.
I'm a little puzzled about this not
Yeah,
converging.
yeah, just yeah, this one. Yeah.
Mm.
So,
What is
so,
different? Because there also unsure answers are all false.
so
You
here
still,
it would not matter because you're using SAT based membership queries.
mm. But why did it perform better in the
In this
top
one,
left-hand corner? Yeah.
yeah, because when you have unsure answers,
Mm.
uh, it gives LLM less like so when you
I'm
don't
not
have unsure
comparing. No,
answers,
no, 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 no. I'm
yeah,
not comparing the
okay,
left and the right. I'm comparing the top
this one,
left-hand corner here and the
this
bottom
one,
left-hand corner.
this top left hand and these two,
No, on the right side.
okay, on the right side, uh, yeah, yeah. Mm.
Why is it that none of the red ones when your carpet budget, query budget is high, is not
Yeah.
reaching the red.
Like here,
Hmm.
this one. Uh,
So what is the difference between the experiment in the top left
these two.
and the bottom
Yeah.
left hand? Yeah.
Yeah. So here, the difference is that in this one, you are not giving all the rules. Like you've skipped the third rule, and this one you have given all the rules. I think it's getting difficult for DFA to learn when it is like when it has more specification. Like that's I'm guessing.
Mhm.
I don't think the paper has dealt with individual these comparison of these. Like they have compared this column and this column. Yeah, like they haven't compared this. But if I were to make a guess, then it's uh it's about like what like if it is difficult to learn the DFA when there are more specification. I
Yeah,
like
okay.
this will definitely have lesser mistakes. Yeah. Yeah. Yeah.
Okay.
Yeah. So, so just to conclude, what we look here is the L-star LM. It's an algorithm. It's a multimodal DFA learning algorithm. It combines LLM with labeled examples and expert demonstration using this. And the correctness, just to note the correctness of this algorithm, it depends on the correctness of the backend algorithms that we are using. Because we are using this just as oracles, and then if our backend, which is L-star, which has a non-trivial proof, but it is yeah, it is correct. So so I tried looking at why would L-star LM will always give correct answer. They were saying that it because of the correctness of the L-star or the other learning algorithms that we're using. So yeah, so leveraging this, just coming back to the conclusion that the this it just bridges the gap between LLM, the knowledge of LLM, that LLM listed knowledge, and the demonstration analysis, uh, which helps us figure out what specifications are important. And then the limitations and the broader impact of future work is like, uh, so reliance on LLM introduces implicit bias, and that may not align with all domains. That and then demonstration help correct such biases. They have mentioned that when you use the, I think I might be overstepping, but I think when the original question that Devanta and you have asked, that if you get a negative answer, I think demonstration helps correct those biases. And while yeah, so the gridwell this gridwell DFA, it applies. So so here we have only looked at the Markov decision process. It can be used like the broader impact, like that it can be used as any learnable class that uh, can be learned using membership and equivalence query. We can extend, like the future work would be to extend this algorithm to other classes such as alternating automata and temporal class. So that's it from my side. Thank you so much. If you have any questions, please.
Yeah, so I have just sort of one remaining question. So this is a question that I had asked some time back, which is
Yeah,
regarding you know positive and negative examples versus expert demonstrations.
yeah, yeah,
Given
yeah,
this whole thing, I mean, see, from
yeah,
what I understand,
yeah,
the LSTAR is going to learn a DFA, where the language of the DFA, I mean, in generally speaking out, idea is to
yeah,
learn a DFA which
yeah,
represents a
yeah,
specification for a certain task. So therefore, the language
yeah,
of the DFA is supposed to be on the labels of the FDP states. That is this based on
yeah,
this sort of marking function, right?
yeah, yeah, yeah,
This feature extraction function is what you call it, right?
yeah,
So
yeah.
so then
Sorry,
the
can you repeat the
DFA,
last sentence?
yeah, sorry.
Sorry, can you repeat the last sentence? I
Yeah,
didn't
so the DFA, so what I'm saying is that the DFA, the language that the DFA is on is, or the alphabet that the DFA is on is all the possible markings that you can have in your
Hmm,
MDP, right?
hmm, hmm,
Like all the
hmm,
possible
hmm.
outputs of the feature extraction map.
Yeah, yeah, yeah,
Okay.
yeah,
So then when the DFA makes a membership query, or when L-star makes a membership query, the membership
hmm,
query is going to be based on this positive and negative examples, and that therefore this positive negative examples at each are going to be sequence of feature extraction function outputs, right?
yeah, 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 yeah. True.
Okay. Now, DISS takes this DFA and some demonstrations, creates a policy out of the out
Yeah,
of the DFA, and
yeah,
sees how likely the demonstration is given this new policy, right?
yeah, yeah, yeah,
So then this demonstration now, if it needs to be checked against a policy, this demonstration needs to be an actual concrete path in the MDP, not a sequence of feature extraction outputs, right?
a concrete path as in, are you saying that it has to reach yellow, or are you saying that it has to be just the path that is defined here, that any path of eta that belongs to the path?
Yeah, so I mean, so
Right.
what I mean is, for
Yeah,
example, in this grid world example,
yeah,
the positive negative examples can be something like, oh, you're allowed to go blue, yellow, blue, but not blue, red,
yeah,
blue.
yeah,
Whereas the demonstration is going to be, oh, a valid demonstration is you start from this square, go up one step, go left
yeah,
and
yeah,
one more
yeah,
step,
yeah,
and so on.
yeah, yeah. That is true. Yeah, yeah, yeah.
Right.
Like,
So
so
these
where the
both of these are
yeah,
sequences of different underlying objects, right?
yes, yeah, yeah, yeah,
Yeah. Okay.
yeah,
Okay. Sure.
and
Sure.
then
Sure. I just wanted to understand
yeah,
that is what I'm
yeah,
getting correct. Yeah. Okay.
yeah, just to add to that, that it where it would fail, it could only be a prefix of a labeled example. Like, it won't be a random path, it will be path generated. It could be just a prefix of a label. Like, that's what they have mentioned, that
Oh, for
like,
the demonstration?
yeah, yeah, the demonstration is the prefix of the final part. Like, that's where uh
I see.
yeah, yeah, or otherwise it can fail because the robot might slip and violates the task.
Okay. I see.
Yeah.
So then, given all of these things, if
Yeah.
is it fair to, I mean, where is the LLM being used? Like, so we
Yeah.
have, I mean,
Yeah.
what, so if I were to somehow take
Yeah.
this work and just get
Yeah.
rid of an LLM,
Yeah.
and want to replace it with some more
Yeah.
traditional,
Yeah.
let's say, formal methods based checking thing, what would that
Yeah.
be? Like, what is it the LLM
Yeah.
giving us extra in this case?
Yeah. So LLM is so yeah, here they have rightfully compared where the left side is where the LLMs are not used, where they have used the traditional SAT solver based
Yeah, but
learning
I don't even
algorithm.
understand
Yeah.
how that works because see, I mean, if we have a natural language query, only the LLM can
Hmm.
parse that, right? So how do they compare it against the search
Uh,
solver then?
so this I don't think I've not come across the paper this
I see.
question.
Okay, so they don't mention this.
Yeah, yeah. I don't, not
Okay.
that of my knowledge. Yeah, yeah.
Hmm.
Yeah. Interesting to think about, but yeah, I don't think the paper has done.
Yeah, because otherwise, how does this comparison make sense, right?
Hmm, hmm, hmm. Right. Yeah, there would be. Yeah. Uh, yeah. I don't think they have like specifically told how they have interpreted the natural language prompt for a SAT solver
Mm-hmm.
based algorithm.
Mm-hmm.
They have not mentioned how they have done. Probably they have used some like techniques to interpret.
I see. So it means some manual interpretation or something like that.
I, I'm guessing. Yeah. This.
Hmm.
I don't think it is covered. Mm, yeah. Any more questions, sir?
No, that's all I have.
Yeah.
Okay, I see. I see. I see. But is one, but I mean,
Yeah.
sorry.
Sorry. No, no. I'm not. Did you say something? Divanta?
No, no, I'm just asking. I mean, see,
Yeah.
okay, so yeah, they're saying that in these experiments, if we compare against experiments, compare against LLM versus non-LLM, LLM performs better,
Yeah.
which I can understand. I mean, of course.
Yeah.
But I don't exactly understand what they're comparing here, but sure. But what I want to understand is, see, where, like, at a more sort of conceptual and theoretical level, where is it that the LLM is helping the whole thing, right? I mean, if I were to, in a world where LLMs didn't exist, would some version of this still be possible? Is what I'm thinking or asking.
Right. I think so.
Because DISs and LSTAR are not like dependent on LLMs at all, right? Both of them are fairly, yeah.
I think so. I think the left experiment is not using LLM. And they might have. I don't think they have explicitly told how they have interpreted the natural language prompts. But yeah, like wouldn't it would be fairly, I mean, at least in this example, it would be easy to interpret the natural language prompts as the
Yeah.
mathematical
I mean, of
rules.
course, you can always take a manual interpretation, right?
Yeah.
Yeah, and then just check whether the positive or like the example whether it aligns well with their interpretation or not. That's all you need to check, right? That's
Yeah, but one advantage while you're, just I was wondering, Digant, that your question, what is the advantage if you start using formal methods, you won't get answers, okay, for big problems, huh?
Yeah, no, so that's what I was thinking, right? I mean, I don't know if that is very readily clear from here. See, because there's several things. I mean, one is that with these LLMs, yeah, they can typically, I mean, the claim is that they can typically take a very, very big inputs. But the reliability drops quite a bit if you, on at least certain kinds of data sets, we take bigger and bigger inputs. And also, there's restrictions with respect to context window limitations and context size limitations and so on. So I don't know if it's necessary that LLMs will, I mean, they scale better than SAT solver, but I don't know if that's an apples to apples comparison is what I'm saying. And then there are limitations to that scaling still. On the other hand, here, see, I mean, there is a lot of, like, there's a lot of, so LSTAR itself is kind of a classical almost formal methods algorithm, right? GISS also seems to be some classical inverse reinforcement learning based method. So given all of these things, is it really the case that LLM is giving us more scalability? Because either of these two things can still be robotic. If the underlying DFA is very, very complicated, then LSTAR will still fail or still get stuck in whatever ways it can get stuck. Similarly, if the demonstrations, like to infer something from the demonstration, if that is very hard, DISs will still fail, no matter what the LLM does, right? So that's why I was wondering. I mean, is it really the case that in this case LLM is giving us more scalability, or is something else happening? Because I mean, if the counter to the scalability argument is that then these other parts of the algorithm bottlenecks, right?
Can you repeat the last, like?
So, like, I mean, so typically what one often hopes with this LLM integration kind of things is that they'll scale a lot better than existing formal methods.
Why are you saying
because
the scalability is not even addressed at least in these pictures here?
Yeah, exactly. That's what I was. That's what my point is. That then, what is it that LLM? So, for example, in typically in things like, let's say, software verification kind of things, LLM are supposed to give you intelligent guesses for things like invariants, and then the hope is that that guess is going to be far better than anything standard formal methods based synthesis like Cygus kind of tool will be able to give, right? So here, what is it the LLM is kind of like giving us in that sense is what I was saying. Like it's not scalability, like you are also saying, like in this picture, it's not like seems like to be scalability, but what is it that they're giving us, right?
Yeah, it just if I were to guess, I think it's trying to provide an alternative to SAT solver based backend. With I'm not. Yeah, I don't think they have compared the scalability here. Like,
I mean, I guess one way to look at it would be that it's simply a natural language interpreter. In the sense that if you have a natural language specification, the LLM simply just checks whether a given. I mean, so basically, at some level, if you want to use a natural language specification, you have to use some kind of a language model that can interpret and understand the natural language specifications, right?
Right.
Maybe that is all that the LLM is being used for.
Right. Yeah. Yeah.
And even then, just at the membership query level.
Yeah. True. Yeah.
Okay.
Okay, yeah. So that's
It's a
all.
very complex
Thank you so much.
Yeah. It's a lot of moving parts here.
Yeah,
Yeah.
lots of them said. I think you did a decent job. I mean, of putting it together, Maya. Yeah. Okay.
Yeah. Thank you so much, sir.
Thank you. Bye-bye. I
Thank
think
you.
I'll
you.
call you
Bye.
later to discuss a few things. Yeah. Okay.
Yeah. Sure.
Okay. Thank you. Bye-bye.
Thanks. Bye.